And yeah, people are coming in, but so Sabina, yeah, you could go ahead, and I guess you are next, right? If I recall, yeah.
Yeah.
Okay. So yeah, our first presentation for the afternoon is Sabina, who is presently a PhD student in computer science, but also doing various things in industry as well as grants. So yeah, Sabina, you go ahead.
Thank you, Prof. Good afternoon, everyone. Well, I am Sabina, and I will be presenting this research, which is a performance evaluation and comparison of a new regression algorithm. And it was done by myself, Chris, and Professor Hussein, and it was presented at a conference, Data 2023 conference earlier this year. So in this research, we focused on the assessment of 5 different machine learning algorithms. So we have decision tree, random forest, KNN, XGBoost, and we compare that with a newly proposed algorithm. The metric that we used to evaluate these was the mean absolute error, and our objective for this was mainly to provide a comparative analysis of these algorithms. So our proposed algorithm was initially introduced to predict insurance policy premiums, basically to balance personalization and robustness in regression tasks. So this algorithm, it basically uses a weighted average of all the samples in the data set rather than the available samples for each feature. The weights are controlled by hyperparameter kappa and Euclidean distance. So this algorithm was done basically in 2 parts. So we had pre-processing, which we normalized the ordinal features, and then we computed the mean target values for the categorical features. So now with numerical features, we imputed the means for it, right? Because, for instance, for like a numerical feature like age, we may have it spanning a wide range. So from like, let's say 18 to 68, which is basically 50 values, right? So sometimes you may not have like, for instance, like for female and male, it'll be easy to calculate the mean, right? So for the numerical features, we imputed the means for those. The prediction aspect of it involved using a weighted average of the target values with the weights controlled by a second kappa value then. So we had 2 kappa values, one for pre-processing and one for the prediction. The optimal kappa values were found using a systematic grid approach, grid search. And the approach here is robust for small data sets or where we have like insufficient samples per category. We also noticed here that, as we can see in the graph, it follows a convex pattern. So initially, as kappa increases, we realize that we see that the error is reduced, and we'll reach a minimum point, and then the error will start to rise again. So we could find an optimal kappa value that corresponds with a minimal error. So for this, we sourced data sets from the UCI machine learning repository, and we used diverse data sets. Pre-processing we kept it pretty simple, where we just removed the missing values and encode the categorical variables. The data sets, we used 7 data sets of varying sizes and data types. So it had continuous, ordinal, and categorical variables as well. Now, we did feature selection as well. So ideally, the best way to find the most effective set of features would be through exhaustive search, but sometimes this might not be feasible. So we used a recursive feature elimination with cross-validation to find the optimal subsets, which is specifically for the random forest model. But we then applied this same subset across all models just for consistency. And each model now may have its own unique set of ideal features, but we use this same set of features throughout. And we also noted that the proposed model wasn't given any advantage in the selection process. So we ensured a fair comparison with the other models. Now to the performance results of it. So we compared it over using the 7 data sets, and we used the mean absolute error with a tenfold cross validation. And what we found is that the proposed method outperformed all the other methods in each data set. So now we had, in terms of people, we tried to compare the performance as well as the runtime analysis with it. And it had a much longer computation time, but this was before we did some optimization on it. So I think Kevin did some optimization where on the algorithm now where we have, I think it's about like probably a data set size of probably 1,000, that the runtime is comparable to the other algorithms. So in this, so what we compared the 5 regression, we compared the 5 models and using the weighted average, and we hear that it outperformed all the all the other algorithms over the various data sets, which demonstrates its potential for application in other industries and real world scenarios. Here we see that the MAE was actually about 45% lower than the KNN and 16.5% lower than the XGBoost. This was the average. This would have been the average performance over the 7 data sets. And for future work, so we're looking at working on using, so right now we're using 1 kappa value basically for the entire data set. So now we'd look at probably specific kappa values for each feature. And some methods, the finding the optimal kappa may have been probably computationally expensive in terms of it would have taken a long time, and try to find methods to find the optimal kappa, which I think work has already been done to or is being done to find the optimal kappa. So we see that this new regression algorithm is robust and can be used. So far, it's has been performing well and can be used for many other regression problems, and we can apply it across several domains. Thank you. Any questions?
Oh, yeah, thanks, Sabina. Any questions for Sabina? So Sabina, basically tried the kappa algorithm across multiple data sets and compared it with multiple traditional algorithms. Of course, it'd be best to have independent evaluation of the algorithm. We don't want to claim it's better than the others. We've shown it across some data sets, but yeah, so she'll continue working on improving the comparison and ensuring that we could defend any claims we make. Kevin did a similar thing for classification as well, but that is has been submitted to a journal, so we're just waiting on that outcome for that one. Okay, good. All right. If no questions, I see we have quite a few new people here. Next is Warren. So this is another case of MSc thesis converted to a conference presentation. Yeah, all yours, Warren.
Okay. Hi, everyone. Can you all see my screen?
Yeah.
Okay, cool. Right. Good day, y'all. I am Warren O'Connell, and this is some research I would have done in my MSc in data science at UE. Right. The title of this is a cognitive automation system to classify and respond to user request emails. Right. Okay. So for this study, I looked at a regional insurance company that has multiple business units operating in multiple Caribbean countries, right? They have this service desk solution that is aimed at managing requests made from one department to the other across the group. Typically, these requests are initiated by sending an email to a specific mailbox like say for example, servicedesk@company.com. And right. And that would lead to an automatic creation of a request or a ticket in that service desk system. Right. Once that ticket is created, there is a tiered support system that the request has to go through. So there's a tier 1 support, which is general IT support, and they are primarily responsible for analyzing requests and directing them to the relevant teams. For tier 2 support, if they can't resolve the issues themselves. So for this, I focused on one particular tier 2 support team, which was a team of software developers who dealt with some of the operational systems. Right. So the challenges we have here is that when a request is sent to the service desk, those analysts have their queue of requests that they have to analyze and assign to other people or resolve, right? So there's a wait time in waiting for your request to reach the front of the queue. Then if the request is incorrectly routed, there could be additional wait time introduced within the process of waiting for the person, waiting for that team that it was incorrectly routed to realize that it's meant for another team, and then for them to reroute it. This was shown to cause reduced trust in this service desk system because of the lengthy wait time. So what would happen is people would then send the requests directly to the individuals who they know can resolve the request. And what would happen is, as a result of this now, we see requests can get missed due to inundation because email is not a suitable place for request management. And we could find that the wait times actually become even longer due to the unavailability of the person the request was sent to. So the goal here is to create an autonomous system that could read the emails, classify them as whatever type of request they are, and then actually respond to them, right? So you could see here in this, this flowchart basically describes that the new email comes in, and this email could be a request, it could be another system. It just, yeah, it's just a matter of how the system is configured, right? Once that is done, they'll be classified, and if there is an action to do the action and then respond to it. So in the research that I found, I discovered that there were some people who did a study on another service desk in another company, and for the purpose of assigning resources or people to resolve requests, because that was shown to be a problem in that company. In the analysis of the requests, they showed that typically when the human analysts assigned the request, it was 85% accurate. So I use that as my benchmark of accuracy for this study. They also got the best performance from using the multi-layer perceptron and the support vector machine algorithm. right? So that is what they did for classifying the requests. To take it one step further, I wanted to actually be able to respond to these requests, and that is where the cognitive system came in, because that is when you combine basic automation with some machine learning techniques or cognitive automation. And when you bring those two together is when you get a cognitive system. So we identified 6 typical issues that they get throughout the year that tend to be repetitive in nature to resolve, and also low impact in terms of like if they were classified incorrectly. And we took emails from over 1 year and labeled them to train the model. So from these, right, within these emails, we would have done some preparation on some pre-processing, which would include substituting staff names for team names, replacing entities like known entity names like servers, policy numbers, ticket numbers, environments, agent numbers, and other email addresses, so that we move away from targeting individuals and more toward targeting teams or systems instead of like an individual policy, like to generalize this, to generalize the scenario basically for the purpose of prediction. Right? Then the words were stemmed, converted to lowercase, special characters removed, extra white spaces, and stop words were removed. So to train this model, TF-IDF was applied to the subject body, the copy field, the sender and receiver of these emails, right? And as mentioned before, like even in the subject and the body and wherever, that individuals' names were replaced with team names where possible. And other people were just replaced with like a general placeholder that says they are staff, right? The output was scaled, and then the multi-layer perceptron and support vector machine were compared with unigram and bigram text representations from the TF-IDF, limiting the length of words to either 15 or 20 characters, because there were cases where basically words longer than that tended not to be real words, and they weren't easily identifiable by like a pattern because of like special characters and stuff in between. And I would have used 5-fold cross-validation, to measure the performance. So one of the first things that I came upon was that when using the bigram representation, the training time increased by multiples. So that was abandoned shortly after, and unigram representation only was used. When looking at the results, we would have seen that in identifying a request, I guess one thing to mention is that within the requests, there are also cases of emails that are not requests at all, or even emails that are replies on requests, and those should not be classified as new requests. So, so from these, we could see some instances where these would be the stemmed words here in some of the cases, right? So we could see at the beginning here, where we see _B here, that means that the word appeared in the body of the email. So we could see morn, assist, good. So it's like, good morning, please assist with blah, 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 like to a developer. And I guess that was like the most important thing when determining that somebody was making a request to the team, right? Right, you could also see here that it was important who the request came from, whether it was another developer or some other user. Right. Good. So once we have the classifications now, using these problems, what I wanted to do was actually respond to the request. So in a case like this, what I would have is a template, and I would query all this information from the database, insert it into the template, and give a comprehensive response about the situation on, for this example, whatever is the policy issue. There are also some scenarios that a developer would go through in troubleshooting a problematic policy that are repeatable. So the program would actually do those steps as well and notify the user that something was done, and ideally it should give them some expectation of when they could see the results, because these things tended to run on a schedule. So it was predictable when they would appear once the relevant fix was applied. Right, so you could see here that all of these in curly braces here are just placeholders that would be replaced by the real information, as this is like a template, right? A response template. So this is what like the user would receive after they send in their request. After training, the best performance was achieved with the support vector machine trained with words limited to 15 characters only. We achieved 86% accuracy, which is just over the benchmark that was used for the human level performance of request assignment, and a 92% F1 score. This is what I would have used to calculate the time savings for the developer on the tier 2 team and how much time they would have saved over the year. So I took the total number of incidents and how many were correct to calculate correct, accurate prediction rate multiplied by how long it would take to get the number of hours that would be saved. And then a similar thing was done to calculate how much wait time would be saved by the people who are actually making these requests. So you could see, for example, on this line here, UAT, where UAT means user acceptance testing, those problems that would be reported tended to be blocking problems. So if one person experienced a problem, the rest of the team would be halted basically from doing what they had to do. So we could see that there are 10 users here. Similarly for this one, CA, which is client acquisition, if this was a reporting thing, if they did not get their reports, the team couldn't do what they had to do for that specific report. So I would take the same 3 things from before and just add in the number of users who were actually affected by having to wait for this thing to calculate how many hours they would have had to wait without the system. So for the tasks that were successfully automated, the longest one took around a minute, which is a huge saving on the hours that the person would normally have to wait. In total, around 260 man-hours could be saved in the tier 2 support team, so that a developer wouldn't have to do that much work on their own, and the system would do it, allowing them to focus on other tasks and reducing their interruptions throughout the day, and about 2,400 hours in savings in man-hour savings and wait times for the customers of this tier 2 support team. Right, the additional benefits of a system like this is that the developers and the service desk team could focus on higher value tasks, and it will allow users to actually build confidence in the service desk support process, which is shown to be lacking now based on them emailing people directly. Users will basically get much improved support without having to learn a new system, without having to send their requests in any particular format. They would do the same thing they were doing all the time, and then they would have shorter wait times. And even for tasks that are only meant to assign individuals or teams within the service desk platform, the service desk analysts will see a reduction in the amount of analysis they have to do. So in conclusion, we were able to build a system that could classify service desk requests for these problems for these 6 problems that we chose to address with 86% accuracy using support vector machines. And they were also able to successfully extract information from the messages using, I guess I didn't mention this before, but they would be able to extract stuff like policy numbers and the server names and stuff like that using regular expressions. So the system would be able to extract information from the message and then do queries in the database and even do some autonomous addressing of issues like doing data correction to make sure that a job could run properly, or just updating a field in a database to make sure some processing can be repeated and different things like that. And then finally, the system can after doing the classification and the actions, respond to the requester with the new information in a much shorter time than the service desk analyst or tier 1 or even tier 2 service desk could respond. And that is the end. Thank you for your time. Thank you for listening. And thanks, Prof, for including me in this.
All right. Thanks, Warren. Any questions for Warren? Yeah, as usual, give your virtual applause. So Warren is another example of somebody doing their MSc thesis. They were able to solve a problem within their job. So they got credited for that. Then they use it for their thesis, and then they published it. So they won out through 3 ways. I know with LLMs, a lot of this stuff will probably be done with LLMs these days, but the question is, in terms of cost and accuracy, it may be still beneficial to do some sort of in-house unique solution, but it's unclear. Okay, if there are no questions, let's move on to Kivan Rajaram, who is a PhD student. All yours, Kevin.
Okay, thanks for that, Prof. Let me share my screen. Okay, so just confirming you guys are seeing my screen, right?
Yeah, we're seeing. Well, I am.
All right, great.
Yeah.
So I'm going to discuss cost reward optimization approach to bank loan approvals. This was a paper that Professor Patrick Hussein and I worked on, and we recently submitted to the IEEE International Conference on Tech Management. So the problem that we constructed on the onset of this was a very practical one, where financial institutions face the challenge of effectively managing delinquency risks associated with customer debts. These institutions rely heavily on deterministic models, particularly credit rating models and so on, to determine and mitigate the likelihood of consumer loan delinquency. The issue is that these are often not dynamic and are often limited by their rigidity. So to put that in context, imagine you want to borrow some money from a financial institution. They would mainly want to know that you can repay them and recoup their money plus interest. And the returns that they would earn would be based on this interest. So if you're not a risky customer, then great, you have no issue. But if you are a risky customer, but you seem like you will manage your risk, the bank will most likely lower the amount you can borrow to minimize losses or just allow the risk. If you're a risky customer, but you cannot manage your risk, well, potentially the bank will seize assets to recoup the loss or have to write off some of the losses as bad debt, which is bad for their business, right? And if you're a very risky customer, the bank will outright refuse you. So these are some of the concepts that were considered when we looked at this problem and the narrative around it. So when we put together this, the main issue was that they grapple with revenue loss caused by delinquent customers defaulting on their loans or customers rejecting due to risk aversion. So the bank is losing money simply because of delinquency or because they lose potential revenues because someone is deemed too risky. What we attempted to do, and I think we were successful in how we employed it, was we looked at machine learning methods to select the best algorithm for predicting customer delinquency. And just for context, the source data set was about 56,000 observations with 17 variables. And the target feature was, of course, delinquency status. And then when we were able to predict the customer delinquency, this was then used to optimize the interest rates to potentially reduce delinquency. And then we use this to model it on a nonlinear regression model to estimate the returns per customer. So this research demonstrates that implementing the proposed method allows financial institutions to profit from approved loans without being overly conservative. So firstly, and this was specifically focused on overdraft and demand loans, which are typically done from retail consumers. So just think about, if you need a vehicular loan or a loan for personal reasons, these would be your demand loans or overdraft loans. And classification models using various techniques and ML algorithms were used to predict the customer delinquency, and this subsequently allowed us to derive the probabilities of delinquency. So one goal is to enhance the predictive models that can significantly impact a financial institution's profitability by adjusting one of their parameters, such as interest rates, to reduce delinquency. And so we looked at several models, an exhaustive list, and we used the top one, which in this case was the light GBM model, and it gave us a pretty high F1 score there, 0.88. And then the diagram on the right-hand side, which is the confusion matrix, pretty much shows how we would have computed those F1 scores with our actual predictions versus the predicted values. So we got some very good results using these models. And once we were able to calculate that delinquency, which leads us into the second part of our solution, which was the main part, we employed a quadratic approximation of a nonlinear regression model to determine the optimal interest rates. Now, when we looked at the variable performance, or the feature importance rather, we came up with the fact that interest rates were the number one thing that accounted for somebody becoming delinquent or not, right? So it made sense that this would be the parameter that we fine-tune. But it should be noted that this does not have to be the only parameter. You can also analyze factors like loan term, amount borrowed, and so on as other parameters to be tuned. So by analyzing factors like interest rate and loan term under the bank's control, the study identifies the method to predict delinquency probabilities. It is expressed as an expected profit from the loan, and we seek to find the interest rate and term combination that maximizes the return while ensuring an acceptable profit for the bank, right? So we came up with the objective function given by this thing here, where R is the return, PR of T is the probability that the customer will become delinquent when offered a loan of value V at an interest rate of R over a period of month T, right? So pretty much this is the objective function that allows us to calculate the return for a customer. So once we employed this, we found that reducing interest rates to delinquent customers could potentially yield higher returns. And I did a specific cohort analysis on this, which I'll discuss in the next slide. For existing customers, optimizing their rates when it exceeds proposed ones are beneficial, while new risky customers can be evaluated along similar historical profiles to reduce delinquency risk, right? So this is beneficial for both existing customers and new customers as well, and holistically the bank. The integration of predictive modeling and cost reward optimization, it does yield superior outcomes. And again, I did a calculation matrix that shows potentially the amount of a bank or financial institution employing a cost reward optimization can yield. In the data, reducing the interest rate for high delinquency probability customers resulted in a slight decrease in delinquency, however, a significant increase in returns. And one of the things that our study was different from previous studies was that we adjusted the rates to reduce delinquency. And this approach computes delinquency first. So usually people, they would adjust the rates, but we compute delinquency first, the probability of delinquency, and then we optimize the interest rates. So we do it in the opposite way, leveraging the learned behaviors for more accurate predictions and computational efficiency. Additional, and this for me, it could be measurable, but it's just any notion that it's qualitative for now. The findings suggest that optimizing the variables like interest rates can extend to other factors, such as loan amount and tenure. But again, we'll have to compute this to be sure. But also it could address financial distress factors, reducing in less credit defaults and improve returns. So it improves things like potentially like customer experience and boosting their satisfaction, because people can keep like assets. They don't have to lose their assets because they were unable to pay a loan payment, for example. So in the cohort analysis, and recall that the full sample was around 56,000 observations, a cohort of 2,348 customers, they had a delinquency probability exceeding 0.98. So these were people that were predicted to be the most delinquent customers. And they had an interest rate of above 11.9%. And so using the quadratic equation for the nonlinear regression, we predicted the return using the probability of the return and time. The adjustment we made was because their interest rate was above 11.9. 11.9 was the maximum return given the quadratic equation. And so this resulted in a slight 0.1% decrease in average delinquency, which is not a lot, but it yielded a 37% higher return. So just imagine, and this was on average, the decrease in average delinquency, right? With just a marginal change to the interest rate, the return was around 37%. And when we computed what that 37% higher return looked like, it was $7 million in revenue retention for customers that would have been potentially delinquent by simply adjusting their interest rates. And so this is the maximal interest rate return there for the 11.9. So pretty much everyone that was 12, 15, 17.5, 20%. Imagine if they had taken an adjustment to 11.9, this is obviously the maximum version of that, and they don't have to opt into that. And this does not skew behavior, but potentially the impact would have been $7 million in revenue retention. So the current results highlight the promise and potential of integrating customer delinquency prediction and interest rate optimization to maximize returns, offering substantial cost-saving benefits to banks and financial institutions. Optimizing the variables strategically minimize delinquency and enhances customer experience through machine learning. And even with a moderate adoption, these improvements could result in significant revenue retention from existing customers and reduce risk for new ones. Future work would include improving the prediction and mitigation of customer delinquency. So the study's limitation include challenges in identifying enough delinquent customers to actually build meaningful models. So obviously it would have imbalanced classes because we have less delinquent customer behavior to learn from than non-delinquent customers. Suggesting the need for longer timeframes and improved data representation frameworks. Future directions involve incorporating more customer data, like things such as credit scores and transaction details to enhance delinquency score predictions and understand customer behavior better. And further research could explore customer behaviors regarding overall loan rejections, addressing the determination of the targeted profit discussed earlier. And this is what we would have presented at the conference. So if you have any questions, I will feel free. I will take them now.
So any questions for Kevin? And yeah, I noticed for Warren, some people had put questions in the chat, and I didn't catch it in time. So we could probably ask those at the end. But so if you have questions for Kevin, please do it verbally, because sometimes I miss the chat.
I have a question.
Yeah.
A good presentation, Kevin. Really interesting. I was curious about some of the modeling that you showed. It seemed like it had a really good scores. How do you think, like, what was I assume banks have some heuristics already for those models. Like what was the like improvement on the banks side of things, if that makes sense?
Yeah, so I mean, granted that this was taken from known variables, so we didn't do a lot of feature engineering, right? To incorporate and that's why I said for future studies it would be good to include things that could potentially impact what these model scores look like. And then the other issue was the imbalanced classes, right? Like I mentioned, we have more non-delinquent customers than delinquent customers, which is good generally, but it's bad when we want to, make general observations about what delinquency looks like. So I think, just definitely extending our time frames or even creating like synthetic data on delinquent customers just to potentially enhance what the results of this would look like. Because yes, these are phenomenal results, but remember, it's just a very small sample that we would have considered. So I think those are some of the limitations, Stefan, but I think it's addressable, to be honest.
Yeah, thanks. Thanks so much. Interesting.
Any more questions? Yeah, so this is more along the lines of, sort of like personalized loans where you provide a loan specific to that customer, just like we were talking about personalized insurance. Because, personally, I think our banks are risk averse. They tend not to want to take risky or perceived risky, give up risky loans. And so at the end of the year, they look fine, they didn't lose money because of that. But on the other hand, so it looks good, for their bonus, but on the other hand, they've missed out on significant potential revenue as well. So yeah, so that's what we were looking at. Yeah, Sarah, you have a question?
Yeah, just a comment actually. I just wanted to say this is such a unique approach. Just in my studies, so one of my lecturers was studying this, and she shared with us her methodology, and it was with regards to US banks, and I found that the approach tended to be, it was almost like a negative reinforcing loop, right? Where they kind of they to avoid the risk, they give higher rates, interest rates to people who are more prone to delinquency, which I found, it made no sense in my mind. So I found this approach, to be unique, and sometimes I find with a lot of things, I mean, when you really start to analyze things, the answer tends to be way simpler than people make it out to be. And I love how it's just clear that, hey, listen, yes, someone may, if they're likely to be delinquent, it's best in all our interests to reduce the interest rate, make it more likely for you to pay it back, and reduce the risk on our part. I mean, it's just it's so simple that it's brilliant, basically. So very good and very unique. Because as I say, there are a lot of studies on this, and it's good to see that see such great work from a local team. So well done.
Thanks very much for that.
Yeah, I just have a quick question on that as well, just because it similarly it popped up on some other research I was doing, which is, so technically if I'm what would be classed as delinquent, and I'm not sure exactly the features that would suggest I'm delinquent, you reward me with a lower interest rate. But I mean, that is a little bit like it's not equitable, right? Because if I'm bad at managing my credit, so
It would give you a
I'm not a
higher
high
interest
income,
rate. They would give you a higher interest rate.
Yeah, I think you misunderstood, Sarah. The more delinquent you are, the higher the interest rate, because yeah.
Yeah, but what we're suggesting that you do for extreme delinquency is just find an optimal rate that is potentially slightly lower, that will make it more affordable for you on a monthly basis without the bank having to incur significant losses and potential like bad debt or taking back your assets and things like that. So it's not to make like significant changes where it's not profitable. So you see, I would have reduced it to the 11.9%, but no one from the 5 and 10% would move up to the 11.9% because it's not feasible to them, right? So it's taking people that are extreme, but then finding that risk reward ratio and offering them that. So that's what the optimization aspect of it is.
Okay.
Yeah, basically trying to match as closely as possible to what the person could afford. so that they don't become delinquent, and both people benefit, both the bank and the person benefit.
And in,
Yeah,
in, in,
yeah, I think I understood that to the point where it would still be high, but not high. What
Yeah.
I'm saying is that it tends to be a negative reinforcing loop, if you understand what I'm saying. Because if you give people who are more likely to be delinquent the highest interest rate, then you're kind of it's like a self-fulfilling prophecy, right? However, what I'm understanding is more of a mitigation factor where probably instead of giving them 12, you give them 10. I'm just saying, I mean, and maybe, especially if after bad paying for a while. So that's how I saw it, but I could be wrong.
And no, you're absolutely correct. And then what happens as a result of that? Because you lower the interest rate to 10, then you extend out the tenure, right? So that it still makes back the same amount of potential revenues you can earn, just over a longer period of time. So it does take into what Prof used the word earlier, very personalized.
Oh, so you do extend the period.
Yeah, you're not just lowering the interest to make them less
okay.
delinquent, right? Because then that becomes a non-profitable business.
Okay, yeah.
Yeah, I mean, you have three parameters to play with, right? The loan amount, the payback time, and the interest rate. So you want to find the right values for those to accommodate both the customer. Yeah. Okay. Yeah. Maybe. I saw some questions for Warren in the chat. If people want to ask those questions now, we could do that before we move on. Or you could just ask.
I see Warren replying in the chat there.
All right. So okay. So
Yeah.
Warren is replying in the chat. So all right. So we'll leave it at that. All right. Thanks, Kevin. So let's go to the next presentation. This will be Kevin.
Yeah. You could see this presentation.
Yeah.
Okay, so this will be a slightly different presentation, I guess. A lot of the papers before were applied, but I suppose this is a little more on the fundamental side of things, so it's not really applied to any specific industry or problem, but well, I guess it's a problem data representation. So my name is Kevin, and I'm doing my PhD under Dr. Hussein. And we recently presented this paper at IEEE's ICT Mod in Morocco. So just first off, why should you listen to this at all? So understanding data as humans, if you have a set of tables, or it's very difficult to understand, but as a chart, like a pie chart or a bar graph, is very easy to interpret. And similarly for machines, they need data in a certain format, mainly numeric, to understand. And the question we really want to talk about here is how could we represent the data better to match the task that is being performed? So if anybody here does do work with categorical, ordinal, or numerical data, the method we're going to propose here is possibly something you could use, just at the feature engineering stage, or, where you'd normally do normalization or any of those processes. So to get intuition of how it is work, we'll just take a toy problem, consider predicting housing prices, very common for when you're doing linear regression, and we have the number of rooms and we have the location, and then we have prices. And you'll see for 2-bedroom in the city of Gondor, we do have a price, so we're trying to predict that. Intuitively, if you're trying to figure this out, you might say, okay, what does a 2-bedroom in Mordor look like? Does $100. A 2-bedroom in Hobbiton does $450. So in your mind now, you're trying to figure out, okay, a 2-bedroom in Gondor, would that be between $100 and $450, lower, higher, maybe somewhere in that range? Now, a machine has to go through that same thing, or in the case of linear regression, it has to go through something similar, right? Typically, what someone might do, or a lot of people, I guess, would do, is we do label encoding. So you'd encode each city as 1, 2, or 3. Oh man, this slide is messed up. So you'll see you replace it here as 1, 2, or 3. But the problem with this method is you're automatically saying in the Euclidean space, at least, that Mordor and Hobbiton are further away from Gondor or Mordor, where that may not necessarily be true, right, in terms of price. And if we look at the averages, you'd see that the average price for Gondor is 800, the average price in Mordor is 300, and then Hobbiton is 475. So now you have a little more information by doing the averages of the categorical variables. And you could say, okay, the average price in Gondor is higher than in Hobbiton. So I would expect the 2-bedroom in the city of Gondor to be more than 450. Now, when we label and code, we do 1, 2, 3. We take that away from the machine to some extent, right? Whereas if we do this target encoding, which is just the average of the target values, the price, and you encode it as those values, so it would look more like this now, the machine is able to have that extra piece of information to work with. And you could do the same thing for the number of rooms if you wanted to. However, everything I've shown so far is something called target encoding. It was popularized, I think, was standardized around 2001, maybe. What I'm going to show now is something called kappa encoding, which is based on the kappa algorithm you all have been hearing a lot about, and kind of explains why it works so well to some extent. So we're going to kappa encode the X feature, which is drawn from a normal distribution, onto our targets, which is also drawn from a normal distribution. Now, on the encoded data, which is on the graph on the right, you'll see that it has moved the features to be centered around a similar mean, and has also done some level of compression. So whereas, this was ranging from 0 to 10, it's now ranging between 18 to 22. So it's actually compressed the data a little bit. And the way the kappa algorithm works is maintaining the important parts that would map these X features to the Y features. Similarly, if we draw from a Poisson distribution for the target, you'll see it does redistribute the X features to look sort of Poisson. So how is this done? This is the equation. Not too much to take away here, except from the fact that there's a weighted average of the target values based on the Euclidean distance of the sample points. And what's really important is this little kappa value here. And that's why it's called the kappa algorithm. So diagrammatically, what that equation means is this. If we have a new point, or any point, we take a weighted average of all the points around it. And then this green circle represents kappa, which is sort of like a threshold, but not like a discrete cutoff. It's a little more of a gradient. So if you plot the kappa functions with different kappas, you'll see it's continuous. So what it does, it assigns a much lower weight to these values that are outside of the region, but it doesn't cut it off entirely, unless it's really far out, at which point you'd be somewhere here on one of these curves. Other thing to note is when kappa equal to 0, you'll see it's a flat line, and that basically means we're taking a mean over all the target values. And we'll see that here. So these are the same plots from before, but with varying kappas. Kappa varies from top to bottom. The first one is kappa equals 0, and you'll see it's just a straight blue line. So it's actually just the mean of the target values. And you'll see it's centered on 20, which was the mean for this. As we increase kappa, you'll see the distribution starts to spread out a bit. And you get the idea, it might have some case for optimum kappa now, right? Some hyperparameter. So what we did from here now was we took kappa encoding against 7 data sets. We tested it using 4 different regressors and against different encoding methods. And the evaluation metric is mean absolute error. So the encoding methods was, the raw values, min-max scaling, PCA. And we included PCA because PCA does a level of variance preservation, which we see some of that behavior happening when we plot the graphs, that it is compressing it to some way with maintaining relevant portions of the data. And then the final one here is kappa encoding. So the way the average delta MAE calculated is the change between our score and the best score amongst these standard methods. So in this case, it would be 2.323 minus 1.613 divided by the original value. So in all cases, we see a decrease in the MAE, significant decrease, which is good, right? It means we're more accurate. And it doesn't seem to matter the regressor we use, all of them improved. Against the data set, so this just shows the improvements across all the data sets for all the different regressors. Again, generally a good increase. So, you could apply this to anything categorical, ordinal, continuous data. In these cases, these data sets are a mix of all three. And we still see improvements across the board. One interesting thing we noticed here was decision tree. The raw was 1.326, and then the kappa encoded was 1.327. So 0.001 more. Similarly here, 0.001 more. And yeah, we plan to do some further work to understand why in both cases decision tree alone didn't have that increase. Maybe the data was already in such a refined form that wasn't able to produce any increases. I mean, Iris is a pretty clean, very controlled data set, so that might be the case for that. The conclusion slide gone. Okay, yeah, so in conclusion, we present a new approach to feature encoding. It works across categorical, ordinal, and continuous data. There isn't much work at all in encoding continuous data because I guess most people take it for granted is already in a form that a computer could understand. But we've seen from this we could get high levels of improvement by moving everything to the same domain and then allowing it to compute. A physics way of thinking about it is you're trying to compute things in different units, which is very difficult to do because you need all these conversion ratios or parameters as we try to estimate them, whereas we do that before here and then allow it to calculate. Yeah,
Right.
any questions?
Yeah, thanks, Kevin.
My video wasn't on. Sorry, thought my video was on.
Any questions for Kevin? So this is going back again to this, this whole kappa thing, and the idea here is to come up with a better distance metric. Interestingly, we also use this distance metric for clustering, but in clustering, you have no labels. So what we did instead is we kind of use a surrogate label and use the same distance metric, and we got improvements as well. I think we have a paper on that here later, I guess. I can't remember, but yeah. All right. Okay, so no questions. All right, so we'll move on to Moisha next. Thanks, Kevin, again.
Let me just share my screen. Yeah. Y'all just let me know if y'all see it.
It's still loading.
Okay. Okay, I'm seeing. Yeah, that's a sec. Oh. Okay, it's saying that my sharing is paused. I don't know why it's doing that. Okay, just let me probably export it and then show it later. Just give me like 2 minutes. Or if someone else is ready while I download it, we could do that as well. So we don't back on time.
All right, well, I see Jamie is here, so let me just see if Jamie was next. I think yeah, so Jamie, you want to go ahead? So Jamie is actually a PhD student not at well, she could talk about her background, but she has two presentations. Well, actually, I was supposed to present one, but I was able to convince her to present it for me. So she will do two presentations now. Jamie, you there, right? Jamie? Okay, I guess she probably thought she's not up next, so let me see. All right, is
Hey,
Ken?
bro, if I could go, if you're ready. Well, I could go on.
Chris, who wanna go, Ken or Chris?
Anyone.
All right, Ken, you go. You were supposed to be after Jamie, so Ken, you go, and then we'll go back to Moisha.
Okay. Let's get in presentation in case. One second. Let's go. Afternoon, everybody. You all can see my screen and hear me clearly?
Yes, yes.
Okay, great. Let's have to do the video. All right. All right, let's get started. Okay. Hello, everybody. Pleasant good afternoon, and thank you for joining. My name is Ken Manohar, and I'll be presenting on this topic on improved distance metric for clustering. This paper was presented at the IPT Mod conference a few weeks ago. So in this research, we focus on the topic of clustering, but with the aim of generating more clearly defined clusters. And specifically, our contribution lies in the area of feature scaling. Right. So to provide some context, well, you're all familiar with the typical machine working workflow. You start from data collection and you go all the way to the evaluation. And for our purposes, is in the data processing step, we know is an important one to improve the quality of the data. And it is here that we introduce a novel feature scaling approach. And we compare its performance against traditional ones like standardization and one-hot encoding. Our approach uses a robust weighted average, which is influenced by the distance between sample points in the data set. And our objective is to determine whether this approach results in more clearly defined clusters. Right, so this work builds on the prior research from Prof. You all been talking about it as a kappa algorithm. And be familiar with the property of this model is where you choose a target label, and then all the distance calculations are performed in terms of this label. So effectively, for each feature in the data set, the feature values are replaced with a corresponding weighted average value in terms of this label. All right, so just to introduce or go over this concept, we're going to use a couple illustrative examples. This is just for example purposes, this is the scenario. So we have a bank, it wants to segment customers based on their balances. You want to have high customers, identify customers with high balances and customers with low balances, right? And you want to figure out like what characteristics separate these customers. So we can use a very simple data set. Let's use a simple data set with just gender, and we have 40 customers. And for males, we have a normalized balance of either 0 or 0.5. And females, we have a normalized balance of either 0.5 or 1. So if you apply any standard clustering here, you will get 4 clusters, right? Represented as the 4 clusters on your right. Now, with the new approach, what we want to do is we want to select a target label. So in this case, we have balance. Balance we'll use to select as our target, and we'll represent all the features in terms of balance. So in this case, we really just have gender. So how we transform gender into the terms of balance is that the average balance for males is 0.25 and the average for females is 0.75. So basically the new approach is that we'll be replacing the gender value with this new average value, right? So basically males are replaced by 0.25, females are replaced by 0.75. And if we apply clustering now using this transform values, in this scenario, we still end up with 4 clusters. So in this example, there isn't any difference between the traditional approach or the new transformation approach that we did. However, if we look at an example of where this time males and females are statistically identical, so you don't really have any difference whether you are male or a female. So in this one, if you use the standard approach, notice we still get the same 4 clusters, right? Males 0.5, males 1, female 0.5, females 1. Now, when we do the transformation, right, this time we're replacing both males and females have an average of 0.75. So we'll be replacing male with 0.75 and female with 0.75. And now when we apply the clusters based on this transformation, we'll get 2 clusters represented in blue, as opposed to 4 clusters previously represented in red. So here we see the difference between the standard approach and the new approach. The new approach accounts for the situation of gender being statistically identical. And in this case, it better represents the situation where a feature has little influence on the resultant balance. All right, so just to kind of summarize the example, so you see it side by side. So what we have done is we have scaled the gender feature and we transform the values and those represent our new distance metrics. So in example 1, where gender was statistically different, meaning that male and female had some influence on their balance, it still resulted in the 4 clusters. But in example 2, where gender was statistically identical, meaning that whether you are male or a female did not have any influence on your balance, it resulted in 2 clusters. So this difference with the new approach can be leveraged as a measure of similarity or dissimilarity between the different data points. And using this new approach, we can more accurately incorporate the influence that a specific feature has. So we did this example running just one feature, right? But how now do we expand this to apply to multiple features? So this is where we come back to the kappa algorithm. So just to kind of run through some of the things, right? For any data set, what we do first is that we have to identify a quantitative feature as a class label, right? This is our target, so-called target. And then for each of the remaining features, we calculate the average label value for each feature value, right? Just like we did in the example. So if you have gender, age, etc., you calculate all those in terms of balance. And now the difference, or essentially the distance between any 2 data points is defined as the difference between their average label values. So effectively, we have these new transform values and you find any Euclidean distance between them. And where the robustness comes in is that the distance is calculated across all data points. So how we saw previously, like in a train test split, if you want to make a prediction for a single test sample, you would find the distance between that, or calculate the distance between that test sample and all the training samples, right? Now what we want is that at the end of the day, we want the samples that are close together to have greater influence than the samples that are wider apart. And this is where the kappa algorithm would have come in, the kappa parameter would have come in, this hyperparameter, because basically that, when we raise the distance, the Euclidean distance calculated to the power of kappa, that basically magnifies how close or how wide the data points are, right? And this is where it originally started in terms of the trade-off between personalization and robustness by adjusting that value of kappa. And in terms of applying it as a weight, once we reciprocate it, we can use this to represent weights. And then we apply the weights to the labels to get the sum of the weighted labels, which is our numerator. And for normalization, divide by the sum of the weights. And this is how you end up with the robust weighted average. So effectively, whether it's one feature, or whether it is a numerical feature or a categorical feature, and when it is multiple features, we just apply the same approach of selecting a target label and then converting all the other feature values, transforming them in terms of this target label, and you can calculate the distance based on the averages you generated. Now, coming back to what we discussing here, which is the clustering, we have the standard approach, which is like a standardization on your one-hot encoding, and this new approach where we transform the values and we use that now to scale the features. Both approaches have some similarities, right? Both of them transform the data set before passing it to the clustering algorithm. Both ensures that features with large scales do not dominate the clustering process. And that way now the clustering is based really on the distribution of data instead of the scale of the features. However, where the new approach stands out is that instead of preserving the relative distance between data points, by this transformation improves the distance between data points. And instead of features being scaled on their original dimension, whether it be, for example, currency, kilometers, and those sort of metrics, all features are scaled in a common dimension, which is whatever we choose as the label. I want to present some of the results when we compare the traditional approach with the new approach. But just to give some context before we go into the results, is that we tested across 3 data sets, right? We call them auto, insurance, and student. And in this case, and I'm proud to have mentioned it in one of the comments earlier, because clustering is an unsupervised methodology, we don't have a specified target as such. So we have to choose a surrogate target or a surrogate label, right? So we look at any quantitative feature, and the most likely one we use as our surrogate label. And for our experiments, we just wanted to do some of the more common traditional algorithms that pretty much stand in the test of time. So for algorithms, we use k-means to represent the centroid-based clustering models. We use algorithmic for connectivity-based models, and we use dbScan for density-based models. And we have quite a number of different metrics. We want to use multiple metrics to try and see how it fares across and not just one metric. And we use silhouette coefficient, Kolinsky, and Davies, right? Right, so on to the results. So first, we're looking at the auto data set, and we're looking at just the silhouette coefficient scores for the auto data set. So the red column represents the standard approach, and the blue column represents the new approach. So just by looking at the chart, we can see for the k-means algorithm, the new approach had better performance in terms of the silhouette coefficient. For the algorithmic algorithm, the new approach had slightly less, about 2% in terms of performance. You know, you could argue that is negligible. And for the dbScan, what we notice is that the traditional approach did not form any clusters. However, after transformation with the robust weighted average and applying the same dbScan algorithm to that instead, it created not a perfect, it did create clusters, but what we call overlapping clusters, meaning that some of the data points could possibly be in different clusters, right? But that is why it have improved in asterisks, right? So we did not end up with a single cluster. We still end up with some type of clusters, right? In terms of tracking, we had recorded all these scores in this table, and what we're going to do is just going to build them out bit by bit so we can get the overall picture to see whether the new approach is really better than the traditional approach, right? So what we did is we just looked at the auto data set, and we looked at the silhouette coefficient. So now we're moving on to the Kolinsky. And we saw that generally the new approach was better than the traditional approach. And we have the respective scores that goes with it. Similar thing with the dbScan, the new approach had 1 cluster, whereas the dbScan did form at least 2 clusters. And with the auto data set, similar type of behavior. And I'll just to note that for the Davies score, a lower score is better, right? So don't mind seeing the blue chart lower than the red. This is good in that case. But basically what the Davies index indicates is that the new approach had better clusters or created better clusters with this approach, right? So basically for the auto data set, generally the new approach was good. And not to rush anything, but just kind of running through each of the others, we begin to see a similar pattern, right? So for the insurance data set, the silhouette coefficient, basically the same pattern in that the new approach was performing better than the traditional one. Same thing for the Kolinsky index, and similarly for the Davies index, right? So for the insurance data set, everything was looking good. The new approach performing better. And our last data set we used in the testing was the student data set. And here we see the same thing, but specifically for the DB scan, neither approach created any clusters according to the silhouette coefficient, right? And when we look at the Kolinsky, same thing, the K-means algorithm that created clusters, the new approach was better. The algorithm created clusters, the new approach was much better as well. But for both of them, the DB scan algorithm did not create any clusters, whether it was the traditional approach or it was the new approach. Same thing for the Davies index, right? So putting the table fully together, all right, and we can just visually see that overall the new approach was much better or performed better in terms of all the different performance metrics that we were measuring against. And for the DB scan, that was really, when we delve a bit deeper, that could be almost attributed to a property of the data sets that we use in terms of when we check the uniform distribution using QQ plots and so on. You see that the data was kind of generally uniformly distributed, which makes it hard for the DB scan to form core regions and form density-based clusters. All right, so that was the general in terms of we kind of understood why the DB scan performed the way it did. And for the other algorithms, we saw that they were better in terms of using the new approach, where we transform the features using the robust weighted average, versus the old approach, where we transform the features using the traditional standard scalar and one-hot encoding. Right, so in conclusion, we are satisfied that the new approach, which is a robust weighted average using that as a district metrics, and that district matrix is influenced by the distance between the data points, that approach performed better than the traditional feature scaling approach in terms of the data set that is transformed with the standardization and the one-hot encoding, and the other data set that is transformed using our new approach in terms of where we found the robust weighted average and represented all the features in that dimension, that the new approach created much better clusters. And different scores were attributed in terms of things like cluster structure, in terms of how close together points in a cluster are versus how far apart different clusters is, and those type of other quality metrics. Based on the scores, the new approach performed much better. So we can say that our objective has been met. In terms of the future work, we need to expand the data sets that we use to see how generalized this approach is. So we want to look at other data sets with other features. We want to look at compare against other clustering algorithms, because there are improvements to K-means, and there are improvements to DB scan, like optics and HV scan and so on. So we want to compare against those newer variations. And also, in the case of clustering, where we have to choose a surrogate label, we can also experiment that across different surrogates, across different quantitative features, right? So instead of just choosing the feature that seems most likely or almost more naturally as a label, we can check if we choose other quantitative features, what impact those have on the clusters. And another future work which actually has started is looking at the optimal hyperparameter. So we know that kappa, and Kevin would have touched on the kappa, how we show the visualization in terms of where it uses a cutoff point to kind of determine the robustness and so on, or how you could choose how robust versus personalized it is. That is a very computational expensive approach to find different values of kappa and then trying to find which is the most optimal one. So there's additional work which I believe Prof will present on later on, where a successive quadratic approximation was used to try and find the optimal value for kappa. All right, so hopefully I didn't rush too much, and at least I was able to convey some of the information clearly. Hope you found it interesting, and can take any quick questions.
Yeah, so questions for Ken? So yeah, so there's quite a bit of work still to be done here, figuring out how to choose the surrogate label, but if it's not too much work, you could evaluate try each of the quantitative features in the data set. Okay, so that's as I said, that's ongoing work. We have some preliminary stuff on optimization of the parameter tuning as we will discuss later on. Okay, all right, so any questions before we move on? All right, thanks, Ken.
All right, no problem. Thanks, everybody. Enjoy the rest of the evening.
All right, and so let's stick on schedule, and then so Misha, I'll put you in Ken's time slot later on, right? But we'll stick on schedule.
No problem.
All right. So next we have is Jamie. So Jamie, are you here?
Hey.
Oh, hi, Jamie. Yeah, so
Hi.
Jamie will present two papers. She kindly agreed to present one of mine. Well, together with hers. She's a co-author on that one. So take it away, Jamie.
Okay, can you see my screen?
Yeah.
Okay, just let me just get this maximal. How do you do that again? Sorry. Right. Okay, so my screen's good. Okay.
Yeah, it's fine. Yeah.
All right. Okay. Hi, everyone. So my name is Jamie. Yeah, so currently a PhD student. This was some work that I'd done some time before. But yeah, I do, yeah. So my background mostly is physics and biomedical physics, and this work kind of came from that, and this is what I did after my master's. Currently I'm doing my PhD in chemistry in something like quantum algorithms and stuff like that, so it's interesting. I've moved around a bit. So the paper I'm going to present, well, two papers actually, are yeah, so this long title, which I'll just before I explain it, just kind of get into what I was doing before. So at the end of my master's is mostly concerned with analyzing kidney stones. So kidney stones are highly crystalline, so some pictures here. And so we can use various techniques to kind of analyze them. So one of the first techniques that I kind of looked at was was electron microscope, and kind of visualizing what the crystals look like under that. And so you have some interesting shapes, and you see some nice symmetries that kind of are a testimony to its intrinsic order, right? So basically, so crystal structures kind of are like these regularly ordered atoms and molecules. And it's because of these kind of periodic ordering of atoms and molecules, we're able to use some interesting techniques, such as X-ray diffraction, to kind of be able to get some information on that, on its structure. So this technique particularly, what we do is that we have the sample kind of right in the center, and then we have like an X-ray source that's pointed towards the sample. And based on how that X-ray beam is scattered upon meeting the sample, it's scattered at various angles that kind of tell you a lot about what's going on in the material. So for example, so with single crystals, again, the regular ordering means that the beam is diffracted in a particular angle, and then there's constructive interference. And so what we get are these like points where the beams are. So those light points on this side is the angles at the various positions that the beam has diffracted, okay? And so if we had many of these single crystals, so like if we were to pulverize our sample, all of them would be randomly oriented, and we'll get something like these kind of concentric cones, sorry, not scones. And so this rectangular here, I kind of thought I was going to have a pointer. This rectangle here is kind of where the detector kind of scans, and it kind of measures the angles at which it sees these peaks of intensities. So at the bottom, that blue diagram is what you would call an XRD profile. So, and it contains a lot of information. Namely, it tells you a lot of things like atomic positions. Like if you knew what elements are composed in your structure, it tells you atomic positions. It tells you, firstly, it tells you what type of material it is. It's kind of like a fingerprint for a given material. It tells you things like the symmetry in the material. It tells you its crystal structure, atomic positions, and things like that. So it's really important in material science. We can even analyze to get like the relative phase fractions if we have multiple materials in the sample, or like what we call multiple phases. We can even do like quantitative phase analysis, but it requires a lot of work. Okay, so one of the first steps to analyzing diffraction profiles is what we call the phase identification step. And typically this is done, so you could see the red markers represent what we found, a match, sort of like a reference to a database. And so it's done with this the International Center of Diffraction data database, and usually it involves search match. So it's kind of complicated, but this is for a singular phase. So this is a pure single phase sample, and then this is where it gets like multiple phases, and you can see some differences, like the actual reference doesn't perfectly match. Also the intensities vary in relation to the reference. So there's shifting, there's intensity variation, and all those things. Add that with multiple phases now in a sample, and you get a kind of a complicated picture. It's not very easy, especially if you don't know what to expect from the sample. So, so first thing, when you do the search match, you get like thousands of hits. Okay. So, and you're not even guaranteed that your answer, if you're going in with no idea what's in your sample, you're not even guaranteed to get the actual match within the first 100 or a couple of hundred hits, right? I've spent a lot of hours doing this, and it was terrible, right? There's a lot of peak shifting. So our material maybe have some sort of variation from the reference. So that also makes the finding what it is difficult. There's also peak overlapping. So because of imperfect materials, again, we have like the broadening of the peaks, and if peaks are broadened, then they tend to overlap with other peaks, and it's kind of difficult to distinguish. And it's all a trial and error. So again, I've spent like hours doing this, and it was just a lot. So the second step is phase quantification. And essentially in phase quantification, the method that I looked at was the rhetorical refinement method. And you want to exactly model everything that you're getting in your data. So the black line is the experimental data, and then the red line is a calculated pattern. And in this goes a lot. There's a lot. So you have the phases, and you're kind of trying to optimize on various material parameters to kind of get this calculation and try to like minimize the differences. And the outcome is that you can also get like the phase fractions, but you get a lot of other data as well. In fact, it generates like about 50 pages of data for one rhetorical refinement. So here we have just an example of the data collected. Main idea was just like you have the phases and the weight percentages. At least that's the major concern. So pros, right, with the rhetorical refinement method for phase quantification, you have full materials characterization, you get tons of data. things that you don't even need. Right, you get the phase corrections, the difference in the cell, the crystal lattice parameters, all these things. It's also a good confirmation method. So if you weren't sure, absolutely sure that a phase was present when you did the phase identification step in the database, it's a way to kind of exactly model what that phase would look like on your given your instrumental settings. So it's a good confirmation method if you weren't sure with your previous step. It can be extremely time consuming. So I've spent hours, like maybe even like 2 to 3 hours on a single sample if it had multiple phases. So as I say, it's a multi-phase drama. So single phases, like maybe like half an hour doing the REDFall optimization, but like multiple phases, it's a lot. So I kind of wanted to know, in terms of machine learning, like what was out there, how do we analyze this, kind of overcome that barrier? And sorry, I have no reference of time right now because I can't see anything. I'm moving blindly.
That's
Sorry.
all right. That's okay. You have playtime.
Yeah, so kind of evaluated what was going on, and in what way are we seeing in terms of material science, you know, how we use machine learning, and how we use machine learning in terms of X-ray diffraction data. And we got some hits, but it was a lot of deep learning techniques. So mostly phase identification. So most of the works like focus on phase identification. So using CNNs, lots of CNNs, ensembles, etc. And they would like have a data set comprised of like, let's say for reference 17 was like 38 phases, but it's not 38 phases all in one sample. It's just like you can have an option of 38 phases. And, you know, they would have to generate tons and tons of simulations in order to train these deep neural networks. And interestingly enough, there is no reason for kind of overlooking simpler models. I think one of them said, well, we kind of expected that, you know, simpler models would not be able to model it. These same people actually later on, they kind of concluded, at least for the task of phase quantification, that they were trying to augment their data set. So they eventually augmented to 40 million simulations. And they trained a deep CNN and it was still not performing as well. So they said, okay, let's try these other models. And they kind of did that. And they actually found that a simple neural network, just like a single hidden layer, kind of performed better than all the CNNs. And also even better, that they found that other models like the SVM, KNN, random forest, etc., they performed even better than the ANN. So that was the premise, to saying, okay, I could actually dive into this machine learning thing without having to go through the drama of learning how to do deep learning, and kind of like test this on my data set. So eventually kind of like rounded up all the models that you could find in scikit-learn, said, okay, I wanted to test this on my data set to see if it could do phase classification and phase quantification. And in addition, because there was a lot of use of simulated data, I wanted to kind of test that theories, like, is simulated data good? So in addition to the experimental data set, we had the primary data set, which is like just singular phases that I kind of generated. And then the secondary data set contained single phases as well as multiple phases, like kind of like a linear combination of the single phase data. Then I tested various training testing scenarios. So I wanted to do simulation testing. So simulation training, just train with simulation data and do that with simulation testing on simulation data, then training only with experimental, then testing on the experimental, then training only with simulated, testing experimental, then doing a kind of mixed simulation experimental and testing experimental. And we use for classification, the standard metrics, accuracy, F1 scores. In terms of accuracy, particularly looked at, I'll define the exact label accuracy, as in it got every single phase correctly. And if there wasn't a phase, then it predicted that there wasn't a phase, that phase. And then the majority phase accuracy in that the major component at least was measured. For regression metrics, define these three, the mean absolute error. So that's like the predicted minus the expected for the phase fractions for each phase in each sample, and the cosine similarity, which mostly points to like a relative scaling between the phases. So it's like if you imagine it, the phase fractions being embedded in some kind of like vector space, and the vectors are pointing in a similar direction or have similar gradients, implying that they are, the relative phase fractions are more or less good. And then this new metric, which Prof defined, which we call rho, and basically it's the 1 minus the Euclidean distance between the predicted and the expected phase fractions, and divided by √2, because √2 is the max Euclidean distance that you could get because of, if it's completely orthogonal. So, Prof, how I'm going on time?
You're good, going good.
You sure?
Yeah, remember you have half hour because you're doing two papers.
Right. Okay. So yeah, I just want to say longer one. So for data augmentation, so essentially what we had was structural crystallographic files. So we took the raw phases, like in terms of their atomic positions, their known atomic structures, crystal structures. And I used a Python library called PyMatGen that was able to generate what we call line spectra. Then I implemented a augmentation protocol, which was able to give the effect of experimental data. So that included broadening the peak. So from the line spectra on the left, you could see just lines, which is not very experimental. That's not how the diffractometer picks it up. But then we want to implement these various sample effects. So we want to shift the lines bits to simulate real data, broaden the peaks, of course, vary the intensities. That's related to something called preferred orientation, a sample effect. Include a background polynomial, which is a representative of if there's some amorphous content rather than crystalline, and then some noise, random noise. So we did that in one thing. The other one is like using a GSAS2 program to simulate some of the diffraction spectra that are not easily simulated in the other way, like if their peaks are way too broad, for example, and then normalization. So in terms of results, so for the first one, we saw that, okay, so just looking at simulation data, yeah, so SVM and ANN did pretty well. So just look at the total accuracy and the average F1 score. For the ANN, we also see that. So we kind of see like some relative on par performance with that. For experimental data, I think it was the complement naive Bayes and the ANN kind of doing okay. Right, just like this is for the experimental also, just a reference in terms of the various measures. And we just kind of see some general performance in terms of total accuracy. All of the models kind of performed on par. And then it's only a certain naive Bayes, the Gaussian one, that kind of just did poorly throughout, but a lot of on par performance in terms of total accuracy. For simulation training and experimental testing, so for this, we have the SVM and the complement naive Bayes kind of got like total majority phase accuracy for SVM. Again, it's not too different in the performance of the ANN. The ANN was like a certain number, and then the SVM just kind of did slightly better in this scenario. And for this final scenario, the SVM and the ANN. So for phase fraction prediction. Okay, so these are the three metrics, the rho, the mean absolute error, and the CS. We kind of just see that, you know, the KNN and the SVM kind of did good across the various instances, and the SVM somewhat. It's important to note, though, that the ANN and the SVR, the support vector machine, but the regression version, we had to do some post-prediction constraints because a lot of the times they output negative phase fractions, and so we kind of had to correct that afterwards. And so these are the values that we got after the correction. So in summary, so for phase classification, we had some models that kind of performed either superior or on par with that of the simple ANN. And we use the simple ANN because we found that the papers that kind of did look at other models as well as the ANN, like the ANN was kind of the better version than the deep neural networks. For phase quantification, so yeah, so the KNN and as well as the ANN. And we found that traditional machine learning models perform well. They are much faster to train, at least with our data set. And then the typical disadvantages of deep neural networks, you know, having to choose the structure, you know, a lot of training, having to need simulated data. And if we analyze this a little bit more, and the paper goes much more in depth, but it's you know, there's no standardized preparation for the simulated data. It depends on what the experimenter uses, and so there's no standard. So how would you know if this is good simulated data for your data set or not? And yeah, so that's still an open question. Can we use simulated data in place of experimental data? And I think for some of the examples in the analysis, we show that, you know, simulated data was not ideal and experimental data is preferred, but you can get improved performance or improved training for some models when you add simulation data in addition to the experimental data. So that's the first one. Okay. I don't know, are there like questions or just like move on?
Maybe you could do this one and then questions afterwards because it's related stuff.
All right, awesome. Okay. All right, so, okay, so Prof in his strike of genius, sorry, literally overnight, came up with a model. So while I was testing these various standard models, you know, he came up with this model and he was like, check this. I was like, okay, I'll check it. I'm like, okay, this makes sense. So let's talk about phase quantification. Okay, so we talked about using the Radfield method, which was the more complicated, more sophisticated method for phase fraction predictions. So predicting the quantities, but there are other methods. So typical methods for phase quantification include like adding like the sample that you want to test with this thing called a standard. So this is a standard material that we kind of know well in a 50-50 ratio, and then kind of basically contaminating the sample and then taking the XRD scan and then comparing the peaks of what you contaminated with that of the other thing. So this is what we call the reference intensity ratio method. So we just kind of use the standard as a reference to kind of quantify the other phases in the sample, knowing that we know how much of the reference that we put in it. Other ones include, like the Radfield method, it's a whole powder pattern fitting method. So you try to do the full calculation, try to calculate the full profile from scratch by optimizing various parameters and get the quantities out of it. So back to Radfield refinement. So I remember showing you this. This was one of the Radfield refinements that I did. And so a big question comes up like, okay, how do we get these intensities? Well, there's this very complicated formula, a lot of physics in this, and I can't go through it all in detail, but it's beautiful. And basically you want to calculate the intensity I at each point, and it's impacted by various things. So one is the crystal structure. So you see that by that factor F, right? Variations in atomic positions and just like things like that, that kind of impact that factor there. You have also the cell parameters, so the dimensions of the crystal, so the spacings in between what we call crystal, the unit cells, or different planes. So that impacts the kind of shifting. We have larger effects, so the crystallite size, so going from the atomic now to a larger scale, the crystallite size, so if we have large single crystals, then what we would expect is these very, very thin peaks, very sharply peaked XRD profiles, but usually we don't have these large crystals, and physics says that, okay, there's a little bit more uncertainty, and so we get these broadened peaks. So crystallite size impacts that. Then you have things called a preferred orientation. That's if all the crystals are not randomly oriented. And then all the way up to the front, we have these phase fractions. So we have to model all these things individually to get the calculated intensity at each point. But if you go back, so this full pattern summation method basically said, forget all of this calculation and just imagine that the diffraction is just like a weighted combination of all the phases that there are. And then these weights is kind of what determines it. And so the FPS, so I want to distinguish between the FPS and the model that I'm going to present, is that the FPS is not a machine learning model. It just has a data of reference phases, and it kind of compares, it goes through the database and tries to kind of weight, like do a weighting. Okay, so this is a machine learning model that I'm going to present now. So essentially, we have that from equation 1, we have this just kind of a linear combination of the individual phases. So the alpha being the weights, and we want to get the y's, which is the intensity calculations, at that point in the diffractogram. So because we have an angular range, so each angle step would consist of point. Then we want to look at, for example, the sum of square differences between what we predict and what we expect. Use this then to see how to evaluate gradients. So as we as we look at the phases, see how the phase changes the gradients, these square differences. So when we choose a different phase, kind of set that to 0, gradient descent, all of that, to parameter, find the optimal XIJs that kind of do this thing and update. So there's a diagram, so don't get too confused by the formulae. For the testing model, now what we have is we know we've kind of able to predict the single phase spectra. Now we want to find the weights in some testing sets. So we input the data, we want to find alpha hat now. And so we evaluate the gradients with respect to alpha hat, and we do the update. And we want to make sure that, of course, our values, our weights, our alphas, that's equation 6, is non-negative. So that's why it's max between that value and the 0. And then we also want our alphas to sum to 1. So each component could contribute maximum 1, and together they could contribute maximum 1, okay, to the weights. And so in summary, it's kind of summarized by this abstract. We have the powder X-ray diffraction profile that we've identified, labeled, quantified. We have the training, the alphas. So each point, all of our training sets and their weights, we put that into the training model, we optimize, we get something like a spectral matrix for each phase that is possible. Then we do some testing, and we can put in an input scan, and what we get is the output alphas. So we train with alphas, we train with these spectral data, the Y's that's coming in, the features input, and we get this optimal spectral attributed to the phase. So just going into metrics now. So for metrics, the same as before with regression. And what we did find is that the proposed model did do better than the others. Cool, fun, right? Also trained well, short amount of time comparison with other things. So this is an example of the predicted phase weights, which are the reds, and what the actual phase weights were. So you can imagine that if there are 7 possible phases, like each set of bars represents the estimated phase fraction for each of the 7 phases. So together they add up to maximum 1. And they look pretty close. This really kind of depicts that. And then here we have is that we've seen that this is what an actual spectral looks like, would be like an actual experimental example would be what we have in orange. And what the model learns are these spectras in blue. So you can see, at least for where we have actual monophase spectra, monophase experimental examples. So the first, the middle, and the second to last one, it looks pretty good in terms of being able to learn the shape of the XRD profile. So a new machine learning model is proposed that performs, at least for our data set, better than the other models at phase quantification, and the model inherently learns the single phase and XRD profiles from the training set. So I think that's it in conclusion.
Oh, thanks, Jamie, and thanks for presenting my stuff as well. It saved me some time. Yeah, some of my presentations, I had done conferences, so I had them already prepared. So, but in this case, I didn't have anything.
Yeah.
Any questions for Jamie? I know it's slightly off top, slightly different topic to the others. But it's all, same thing. It's machine learning optimization. Basically the last model she talked about was an optimization problem that I enjoy working on.
Yeah. Me too. All right.
Okay. All right. Thanks, Jamie. All right. So let's go to Moisha. Yeah, Moisha, are you there? All right. I guess yeah, I'm not seeing Moisha. So Chris, you wanna go next then?
Yeah, sure. Hold on. Let's share the screen. That's all. Presenting. All right, share screen. Okay, so you guys see my screen there?
Yeah.
All right, cool. All right, so hi guys, Chris Manohar from South Trinidad. So I'm here to present some work that Prof and I did on improving the academic advice given to students by trying to optimize their trade-off between the GPA and the time to complete their course of degree. So where this problem actually came about was, at university, I'm sure everybody familiar with this exercise. Every semester we have this academic advice and thing, right? So basically what that is students come and we have to kind of guide them and see, okay, what core courses they need to do, what electives they need to do based on your past history and performance and so on. So traditionally, what you would do is that it would probably be optimal in this case for a minority of students, and the two student groups would be the weak students who just really have 3 options, and most of the times there's not much variety in there, so they just need to do these things, and then they have the strong students who perform well. No matter what they do. So the course selection, academic history kind of thing is sort of doesn't really apply to these guys. They would always just do well. Right. So, but that's only in the edge cases. So the majority of the students, which are what I call the average students, there is something to do there, right? because if they were to do more courses, they may be able to pass, but their quality of grade might drop, like from A average to B, right? Whereas some of them to do more, they would tend to fail, as if they probably just did 4, they would pass on, so on. So there's some trade-off here between the completion time and the quality of grade, right? Which are the two main concerns. So the question that we had here is, can an advisor accurately guess, so let's say some students, Bob's overall performance given his current course selection, right? Now, of course, this is easy to do if you had like 1,000,000 Bobs, right? Because if you have 1,000,000 Bobs, it's pretty robust. You just sort of take the average of all of them and you're good to go. But it's hard for the advisor, if he doesn't have 1,000,000 Bobs in his head or haven't met 1,000,000 Bobs, to be able to estimate his performance. So typically what you do is that you would estimate his performance based on an average student, right? So you're saying, okay, generally in the past, historically, this course does blah, or students like this do whatever, and it's okay, this is what you would do. But that may not apply to the current student, right? Because they may be slightly different than average, right? And also, the other thing that they would do is that they would try to advise him based on the few Bobs that he remembers from the past, right? So now, while this may be a little bit more personalized to who the student are and his performance, it may not be a robust piece of advice, right? Because it's like basically it's rolling the dice because you don't know if this person is like one of these 10 people that you met before. So the approach I decided to take was following the same personalization trade-off that we've been discussing for the majority of these papers here using the kappa algorithm. So it's presented in a slightly different form here. Where really the interesting thing about this algorithm is this nonlinear weight, right? So essentially, when you're trying to predict the grade, you're trying to predict the grade, so using the hyperparameter kappa, and essentially what it boils down to is just a weighted average. So here we can see the weighted average formulation, right, where the weight is given by the 1 over 1 plus ds to the kappa, right, where ds is the distance in terms of the common metric space, in this case would be average grade, right? So what this shows is that for the prediction for any one course for Bob, right, is not just based on Bob one history alone. It's based on everybody. So every single person in the entire data set contributes towards Bob's prediction of a grade, right? So that makes it robust. And the kappa parameter is what makes it personalized, where we have that kind of smoothing function. So we only pull sufficient. So for the value of the kappa, we pull values that are pretty close, students that are kind of like Bob, right? And those are not like Bob, they still have some influence, but very little. All right. So basically, as kappa tends to infinity, you get maximum personalization, right? Because the weight essentially goes to 1. But when kappa is 0, sorry, the weight goes to 0. But when kappa is 0, the weight goes to 1, which means you treat everybody's influence as exactly the same. So it's basically boils down to the average student mark. All right, so how would you compute this distance? Well, basically, we just converting it into the means mark space. So what does that mean? So for example, you have an attribute gender, right? We say, okay, what is the mean of all males in terms of their marks? What is the mean of all females? And that will be the mu male, mu female. So if I'm a male, and comparing with a female, I'll take the difference with that. So that what that means is males like me, the distance would be the ds would be 0, which means the weight would be 1. So I would trust males, right? But if it's females, if they are similar, just like males, so if it being male and female didn't matter, what would happen is that this difference here would be 0, right? Which would be the same thing as if it were males. But if it did matter, then we would produce this distance, which would then scale using the kappa algorithm to give us the weight, right? And the same thing for courses and all any sort of attributes, right? So the key idea here is that this converts everything now into this common metric space, so this grade space. So we can now compare and group students fairly, right? So what essentially happens is that this WS kappa is basically Bob's personalized weight for some other student, Mary, right? So when you do this thing, and this is why, so the problem, one of the issues we have is that this thing it takes a long time to run, right? We'll talk about it later. But basically, for each person, what we need to do is compute a personalized weight for every single prediction, right? And but is that personalization that gives us zero robustness, right? Because that way we don't throw away any data, we use everything from the data set, right? And the nice thing about it is that these weights are self-adjusting, as I explained. If the gender didn't matter, then the means would be the same. So in which case the distance would be 0. All right. So that's kind of like how all that sort of fits together. All right, so in terms of the computation, what does this mean? Unfortunately, means for every Bob X, we have to compute the weight for every Mary in the data set, right? So basically, the runtime scale is an order n squared, which can be to tune this kappa is really expensive with a grid search. But yeah, we have been doing some works where we showed so Kevin and I think we did some work with Ken and Prof and how we could tune this parameter using quadratic approximation or just using GPUs to get the runtime down, right? So while it's expensive theoretically, there are ways in which we could sort of estimate it in a quick time. Right. So in terms of the data sets, how we applied, so we took grades from our undergraduate CS and IT program. So we had about 13,000 grades, roughly about, so it's a bit imbalanced. Most of these students in field was about roughly 1,000 field. Right. The features that we had access to were things like course code, prerequisite grade, degree program, number of courses, etc. Right. And the data span 19 semesters over roughly 1,000 students and 200 courses. Right. So basically, how are we gonna, so it's a time series data. So how are we gonna analyze the experiment? So it's okay, in terms of prediction performance, we basically want to see how close we are in terms of predicting the grade. So the mean absolute error was what we decided, and then of course we normalize that to see how better than average. Because remember, generally, an advisor is not gonna have all this information in his head, right? So basically, what he would do is advise based on average, right? His experience, quote unquote, that's basically aggregating information over time. So the normalized mean square basically tells us how better than average this person did, right? So because it's a time series data type, we can't really do the 80-20 split here, right? Because it depends on what you do, you randomly select things to be in the test and the train. But if we do that, then we may have future things for a student, like so a student like his semester of 2010 might be in the train set, but his semester in 2005 might be in the test set, which obviously not going to work, and vice versa, right? So you're going to have some data leakage. So basically how to work with these time series is that you do the fold based on the time, right? So not only data, but only time, right? So basically, once we do that, so we hold out like the last semester or the last 2 semesters, and we use everything else to train. And then based on that, now we predict and measure how good we will compared to what actually happened. Right. So basically, the experiments then boil down into two categories. So the first one is to predict the students' course, because remember, we want to advise them for in terms of they're looking at the semester average. That's the goal, right? Trying to say, okay, if you do this combination, it'll make sense for what you want. Or if you were to put in this one, we could actually see and measure the effect, right? But that's basically an aggregate of their course-specific performance. So the first type was to see how well it did in terms of prediction of the course, and then of course how close did we come? So given the course selections for a particular student, how close did we come to actually predicting their performance for that semester? So here we have the graphs here where we studied each of the features, but in individually, right? So we did the same thing, but just considered, okay, this is just course code alone, prerequisite grade alone, program, etc. Right? And what this graph shows for these things is, and this is how you can do kind of the feature selection, we get to see the influence of each of these features on the objective, which is the predicting of the grade for that particular course, right? For the student. So what we can see here is that in terms of advising a student, what is the most influential factor to consider is obviously the course code, right? Which sort of makes sense because some courses are just, just hard, right? Then of course the prerequisite grade makes the next thing, followed by program. So it's listed in order here. But what's important is I want to observe here is that normally, like when we advise and we say, okay, of course we would consider the course code, right? That's fine. But sometimes we look at not just the previous grade, but also we put a lot of importance on this feature here, which is the previous GPA, right? Because we try to get a sense of, is this student a good student, a bad student? So while that's generally how we would give advice, which we do down here, we see there are many other features that have far more influence in terms of that we should be considering other than just the GPA, right? And of course, the credit rating didn't really matter. And in terms of the gender, we could see here is basically a straight line. So, basically what it was saying is males and females, it didn't really matter what the genders were. The performance is more or less the same for the two, which is good, I guess, right? Now if we combine all of those features together, we get a significant drop in performance,
Yes.
right? So So this is the it's very personalized. The kappa is 5, so that's a good value there, right? So in terms of the actual errors, we said so here we did the test here, so we had like 2 years, and then for the rest, so this is times 3, so we had a split on time, right? So we do 2 years training, 4 years training, 5 years training, and we was able to get the error down to about 7. And what was interesting, and this sounds something for future work, is that if you take out the F1 grades, so the F1 grades are those things that are like less than 30, right? So they fail, but sort of fail really bad, right? What we see is that it actually improves the prediction, right? So what does that tell us is that the features that we capture in currently it doesn't have much variance with students that just do really, really bad, right? So that's one room for improvement. We had to try and figure out um, some kind of feature engineering step to capture the variance for these low performances, right? Performance. Now we're really close. The objective here is really to get it to 5 or less, because the GPA points actually varies into bands of 5, right? So once we can get our semester average prediction within 5, then we're good, right? So that was the result. So what are the limitations? Right. So the current features again have low variance against students who got these sort of failing grades, right? Then of course more features would be nice, right? For it would be nice if we could get. I'm pretty sure if we could get the assignment marks as the student progresses through semester, we should be able to get a good prediction. But this is in the advising scenario, so it might be kind of hard to do that because it didn't do the course yet. So we got to think about something interesting here. So this is a nice problem. For this study, we had obviously limited data because we just did it from one department, although it was over 5 years and a good bit of rows. So what we're doing currently is seeking additional data sets from the faculty to see how that works, and we could try it across other campuses. And another interesting area for future work is that we just optimize on the number of courses and the time to completion as the two objectives, right? We trade enough, but sometimes students might care about the capacity, they might care about some kind of merit level or social value in terms of how they build a degree. Because part of one of the types of degree that you have is a general degree where they have 30 elective credits, and they could do that from any faculty, right? So you could be doing computer science, and you could do social courses if you want, or HR courses. It doesn't matter. You have you literally build your own degree. It's like a subway. So students like those might care about things other than just the degree completion and grade quality. All right. So in conclusion, what we did, we have a personalized algorithm to help with academic advising. So based on this results, we think it's sufficient that advisors would be able to interpret the influence that individual features have on particular grade prediction for a student, be able to personalize the semester's course selection for a student, and then of course optimize between which of these things the average student cares about, the degree completion or the quality of grade. All right, so that's it there from me. So if you guys have any questions.
Any questions for Chris? All right, so thanks, Chris. And one of the issues we have is and Chris and I have been looking at this is behavior. So typically, if somebody knows they are going to fail a course, they stop working on that course. So their mark, they either get like 50 because they pass, or if they know they're going to fail, they stop working on the course and they get close to 0. So there's a discontinuity there that we need to capture better. And I think, well, Chris, I have some ideas we could think about in capturing that, but I think that's where we lose in accuracy. And once we fix that problem, I think we could get within 5, as you said. Any questions? All right, thanks, Chris. So let's go to Moisha. Moisha, are you there now?
Yes, I'm here.
All right, okay. So you go ahead.
Let me share my screen. Okay, y'all could see, right?
Yes.
Just try making it bigger. Okay. Okay, so good evening, everyone. So today I'll just be presenting on the paper that came about from my my thesis. This work was done in collaboration with Kevin as well as Professor Patrick Hussein, who is my thesis supervisor. So I'll just get into it. So a bit of an introduction. So polycystic ovarian syndrome, PCOS, is a prevalent endocrine disorder that affects women globally. Though the exact prevalence of PCOS varies depending on the diagnostic criteria that is used, the World Health Organization, the WHO, reported that approximately 116 million women, which accounts for 3.4% of the female population, was affected by the syndrome in the year 2012. However, it's important for us to note that even though this is the value that is reported, we still have around 70% of women with PCOS who remain undiagnosed. So the issue in having a well-rounded PCOS diagnostic method is that PCOS can have a significant impact on women's health, and it could also present itself in women differently. These symptoms could range from both physical and physiological, for example, irregular menstrual cycles, to infertility, and even things like anxiety and depression. So in doing the research, a flaw with the current PCOS diagnostic methods is that they tend to be very subjective, since they rely heavily on the interpretation of the symptoms by healthcare professionals. Additionally, we see that these traditional methods can often overlook the intricate interplay between these diverse symptoms of PCOS, which leads to a lot of women being either undiagnosed or misdiagnosed. So the whole idea behind the research here is to kind of outline how the integration of data science techniques into the PCOS diagnostic process could help address the issues that I just mentioned. So basically, the objectives of this study were one, to investigate how data science and machine learning techniques can be applied to revolutionize the PCOS diagnostic process, as well as to develop an objective, reliable, and even a more accessible means of obtaining an accurate PCOS diagnosis. So just an overview of the CAPA algorithm. I know a lot of us have presented on it today, so I feel like at this point we kind of have an idea of what's going on, but I'll still go over the slide nonetheless. So this algorithm was used for this study. It's a novel distance-based method which calculates the distance between observations, which in this case would be the woman which were included in the data set. And this particular algorithm, what it does is that it leverages weighted averages and the exponential decay of the hyperparameter kappa to estimate the outcome values or classes. So as mentioned before, the whole idea behind this algorithm is that it was designed to find that balance between both personalization as well as robustness in the prediction process. It is able to achieve this balance by incrementally taking into consideration the information provided by the features and make more personalized predictions as kappa, which is the hyperparameter, increases and tends to infinity. So, though this approach is new to the healthcare sector, it has already yielded promising results in different sectors, as we've seen Prof talk about it, for determining premiums when it comes to insurance. Also, using this algorithm for this study also made sense, since that the kappa algorithm, it sort of aligns with the need for a PCOS diagnostic method that can both deliver tailored predictions based on the various presentations of the syndrome, while still encompassing information from the entire affected population. So, a bit on the methods and materials. So the data set that was used in the study is a partially refined version of a popular PCOS data set, which is used for classification. The data was collected during physical exams and blood tests, which was conducted across 10 hospitals in India. So it contained data for approximately 530 women across 38 parameters, which were both clinical and demographic. So now a bit on the method. So the method, the overview of the method on the implementation of this algorithm can be summarized into 3 main steps. So firstly, it is finding the optimal value for the hyperparameter for each feature. So what this is essentially is that the algorithm is now going to produce estimates for the outcomes using each feature as a sole predictor. And then this optimal kappa value would be the value that minimizes the MSE, the mean square error, across 5 partitions of the data. Then after that, we're gonna find the optimal value for kappa for making predictions, which is very similar to the previous step. And just in this case, we're just taking into account all of the features. And then lastly, the feature selection process. So this is where the algorithm is going to select the most informative and descriptive features for accurate predictions. So this is done by adding in the features one by one and then calculating their MSEs, which is again similar to step 1. So the whole idea behind this is that as a feature is added, if it yields a smaller MSE than the previous composition of features, then it's going to be kept. And if it's not, then it's going to be discarded. So a bit on the results. So the proposed PCOS diagnostic framework, it demonstrated comparable accuracies with an overall performance level of roughly 87% with the following 10 predictors that we see on screen right now. In contrast, when applied to the same data, a statistical model, I think the model I used then was a random forest model. That model achieved a marginally higher accuracy of approximately 88%, with a reliance on more than double of that of the kappa model. I think it was like 23 predictors. So it's also important to note that all of the features that were deemed or that were labeled as important to the model when using the kappa algorithm, these features were a subset of those selected when using the random forest model, just with the addition of the luteinizing hormone levels. So as people have been mentioning before me, in comparison to the other machine learning models, kappa is just a bit more computationally intensive. Thus, we could see work done to optimize this process, but as we've been hearing, this is already in the works, so it's something that we could see added into the use of the kappa algorithm very soon. Also is important to note as well that even though there was a slight discrepancy in the accuracies, the kappa algorithm was still able to achieve a very comparable performance with significantly fewer features than other statistical models. So, which just highlights its superior efficiency and efficacy in extracting and leveraging the most important and informative features for accurate predictions. So very short and sweet as well, so this work was done in collaboration with Kevin as well as Professor Patrick Hussein, and I'll just thank you for the opportunity to present, and I guess I'll just take any questions now if anyone has any.
Oh, thanks, Moesha. Any questions from anybody? So yeah, so actually, so Moesha had done this work some time ago, and so when she came to me, I said, well, let's try the kappa algorithm to see how it compares. So it was interesting work as well, and she used that for her thesis. All right, thanks, Moesha. Let's go to Shelly-Ann next. Oh, any questions for? Yeah, I did ask, right? Questions for Moesha. Okay, let's go to Shelly-Ann now.
Okay, can you see my screen?
Yeah.
Okay. All right. So good day, everyone. So my name is Shalian Suklal, and I will be presenting the work entitled Optimization of Long-Term Profit when Cross-Selling Insurance Policies. And this work was done by myself and Professor Hussein and was presented at the IEEE ICT MOD conference. So for the presentation today, I'll give an introduction to the research area, then I'll go into the research goals, as well as our contributions. Then I'll talk about related work in the area, and then how we formalized the problem. I'll also explain how we tested our methods with real insurance data, and then summarize the main points. So insurance companies try to increase revenue from their existing customers by cross-selling other products to them. And they do this by either running campaigns to push specific products or by selling the product that earned the business the most immediate profits, or by the agent selling the products that earn them the most commissions. So in the past, recommendation systems have been used for this task, and the aim was to maximize profits or commissions. However, there are issues with all of these approaches. They do not consider the suitability of the product for the customer, as well as their likelihood of canceling in the future. And there are a couple cases to consider. So first, if the recommended product is accepted by the customer and is suitable, then both parties benefit. However, if the recommended product is initially accepted but is not suitable, then the customer would eventually cancel the policy, causing loss to both parties. On the other hand, if the product was not suitable and was not accepted by the customer, there's a likelihood that this can reduce trust by the customer and they may eventually move to a competitor. And then from the perspective of profits gained by a policy, there can be policies with high upfront benefits to the company, but the long-term gain is lower than that of another policy with a lower upfront profit. So this takes us to the aim, which is to find the right balance between the long-term profit of a policy and also the satisfaction level of the client. So long-term profits are achieved by considering the profits gained during the lifetime of the policy. So in order to achieve this, we created a benefit-based decision tree, which we optimized with respect to long-term profits, and use this decision tree to predict the suitability of the product for the customer, as well as the customer canceling in the future. So these models were based on customer characteristics such as demographic data. We also propose a method for determining the most appropriate product for the client by combining suitability scores with cancellation probabilities, as well as customer lifetime benefits. We also applied our methods to real insurance data to demonstrate the effectiveness of our approach. So there are some researchers who have performed work in this research area. But for the interest of time, I will just speak about a paper that is most related to ours, which is the work presented by Hussein et al. And they presented an approach to optimize long-term benefit by considering both suitability of the product as well as lifetime profit. So they tested their approach on a movie lens data set. However, the results did not show a clear distinction between the accuracy-based models, short-term profit models, and long-term profit models. Our work extends their work by first not only including a suitability model, but also by including a model to predict the probability of cancellations in the future. So we also use a benefit-based approach, which optimizes based on overall lifetime profits, and we use real insurance data for testing. So I'll now get into the formalization of the proposed methods. So if we have M products from which to choose from to cross-sell to N clients, then we let SMN represent the score of recommending product M to client N. Then for a given client I, we want to determine the product that gives the maximum score L, as shown in equation 1. And the score SMI is based on the suitability of the product, as well as the probability that the client would cancel the product in the future. So this is shown in equation 2, where L star is the lifetime profit of the client if offered the product. And this is calculated as shown in equation 3, where VM is the premium for policy M, alpha M is the depreciation rate of the premium over time, And for policies such as home insurance, where the rate is constant, we set alpha equal to 1. Then the overall long-term profit or the lifetime value of a customer will be the sum of all lifetime profits over all of their policies. So note that both the suitability scores and the cancellation probabilities can be determined using a classification algorithm. And from prior testing, we found that decision trees are the most suitable for our data set in terms of accuracy and F1 score. So it was chosen for our research. And the issue with decision trees is that they train with the aim of achieving maximum accuracy, but we can introduce benefits and costs while training in order to optimize based on maximum lifetime profits. Benson et al. Proposed an example-dependent cost-sensitive decision tree. So we decided to compare our work against theirs. However, their method did not adapt well to our use case. So depending on the goal of the problem, whether it's minimization or maximization, their method classified all samples as either the negative class or the positive class. And then on further inspection, only if we assign cost values and no benefit values when training, then better results were obtained. But this is not desirable for our use case since we want to optimize with respect to benefits or profits, so it was excluded from our analysis. We propose our own benefit-based decision tree with the aim of maximizing overall lifetime profits over all existing customers. So in previous work, we presented a scaling factor eta, which was applied to the cost function of the logistic regression algorithm in order to include costs and benefits when training. Eta is calculated as shown in equation 4, where Bij is the benefit of classifying an instance of class I as class G. The scaling factor eta can also be applied to the loss function of the decision tree classifier. However, we need to determine individual benefit and cost values for each client, since each client has their own portfolio of policies. Therefore, we compute eta for each client. And these eta values can then be applied to the loss function of the decision tree algorithm via the samples weight parameter of the fit function, which is available in the decision tree classifier that is offered by the scikit-learn library. So I'll now explain how these methods were applied to real insurance data. So due to the nature of the data, we cannot disclose all the details, but I'll just give a summary. So the data contains details on clients, their policies, and also their transactions. The data is rolled up at a client level, which allowed us to include summary features such as the total number of policies and total premium. The data contain two types of clients, individual and commercial clients, but for our testing, we only use data on individual clients. And the data range from the years 2015 to present, and data from 2022 was used for testing, and everything prior to that was used for training. And we also created buckets for continuous values such as age and sum insured gross. And we use a one-hot encoding approach to represent the client's policy holdings. And we created flags for specific details on the client, such as if they have home insurance but no motor insurance. So we need to specify the benefits and costs associated with each classification outcome on the confusion matrix, and we need to do this per client and per policy. Also, we have separate models for suitability and cancellation probability. Therefore, we need to create separate sets of profit matrices for these. So let's get into how we came up with the benefit and cost values for the profit matrices. For the suitability model, the true positive case is when we cross-sell a suitable product to the client. Therefore, we set this to be the lifetime profit of this new policy plus the lifetime profits of all the client's existing policies. And then for true negative, where we don't cross-sell the product, the benefit value would be the sum of the lifetime profits over all the client's existing policies. For false positive, this is a case where we run the risk of losing the customer by presenting a product that is not suitable for them. So we set this cost to be the client's total premium over all their existing policies. For false negative, this is the case where the product is suitable, but we did not try to cross-sell, so we lose that initial investment. So we set the cost to be the initial premium of the product. And then the cancellation model's profit matrix is simply the reverse of the suitabilities model's matrix. So for example, what is true negative in the cancellation model? Well, in the suitability, what is true negative in the suitability model will just be true positive in the cancellation model and vice versa. So for our experimentation, we generated the profit matrices for all clients across all policies for both the suitability model and the cancellation model. And then we obtained suitability and cancellation probabilities from first regular accuracy-based decision trees, and then our proposed benefit-based decision tree. Sorry. So for each method, we determined the policy with the highest score for each client, and then we summed up all of these scores and the totals for both methods were compared. And we did the same thing with the benefit values, which came from the profit matrices. So the table shows the comparison of the results of the accuracy-based decision tree and our benefit-based decision tree. And when we look at the profit scores using both the client lifetime profits and the benefit values, we see that our proposed model achieved much higher profits than the accuracy-based model. And there was an increase of 6 million for client lifetime profits and 1.3 billion using the benefit values. And just a point to note, this result is just a subset of the clients in 2022. But if we use all the individual clients and all commercial clients, then this number would be much higher. So in conclusion, insurance companies try to cross-sell policies that either earn the highest immediate profit or commission, but it would be more beneficial to consider overall lifetime profits. The idea was proposed by Hussein et al., and we extended their work by including a model to predict cancellation probabilities. And we also applied benefits and costs when training the suitability and cancellation models. And these models aimed at maximizing lifetime profit. We also applied our methods to real insurance data. We compared our approach to traditional accuracy-based approaches and found our model to produce higher lifetime profits. Right, so this brings me to the end of the presentation. Thank you, and do you have any questions?
So any questions for Shelly-Ann? Yeah, so Shelly-Ann has been working on her PhD towards well, doing work on this cost benefit based approach to classification. And it also applies, she's going to be looking at things like AI bias as well, because it could apply to that. In terms of the long-term optimization stuff, that problem actually came about from work we started with another insurance company. So it just illustrates that, you pick up interesting problems as we work in industry. It's hard to come up with interesting problems if we stay within academic walls alone. Okay, so if no questions for Shelly-Ann, thanks again, Shelly-Ann. So I guess the last two are mine. So we should be able to wrap up on time. Let me share my screen. All right, so this paper here is based on just an idea I had. So my background is in telecommunications. So let me. Is in telecommunications, and there's this issue of overload control, etc. And to me, I saw that kind of happening within academia as well, where we try to bring in too many students, and what happens is students fail, and when a student fails, both parties lose, because the student doesn't graduate, so they've lost their investment. Well, I shouldn't say fail, drop out. So, if they drop out, they've lost their investment. And on the other hand, if, in addition, the university loses as well. I mean, the university gains by financially, but it loses in the fact that an investment was made in resources for that student, and it could have been assigned or applied to a different another student and increase their throughput or goodput. So another way to look at it is look at a telephone system, a telecommunication system. As the load increases, the goodput or rate of successful calls will increase because there are no drop calls. But at some point, as the load approaches capacity, you start, some of the work is wasted on calls that will eventually be dropped. All right, so because of that, you can complete less and less calls because more and more work is spent on calls that will eventually be dropped. All right, because it's a long, so can't get into details on call processing through the signaling network, but this is what happens. So as load exceeds capacity, the rate of successful items drops. And this is what we call the goodput, the rate of successful transactions. So overload control is maintaining a maximum goodput. All right, you want to get to the point where you do not waste too much time on failed transactions. So similarly, in a university system, the input is admitted students, the output is graduated students, and the drop calls would be students who drop out. All right. The capacity is the teacher resources, which is limited. And the student quality, there's another issue is the student quality also drops as input is increased, because since you pick the top students, to increase the number of allowed students, you will have to pick from the lower end, so the quality of students drop as well as you increase the enrollment. So this actually leads to a nonlinear effect. So you have two components: the reduction in quality as the input increases, as well as the increase in work that will not be will not result in a graduated student. So increasing intake to increase revenue may lead to fewer graduates, and if it's a private university, it will be lost in reputation. In case of Trinidad, it's really more of a monopoly. So we could model this mathematically as follows. So let the student intake be n, and the dropout probability be rho of n, or p of n, sorry. So it's a function of n. So the dropout rate increases non-linearly with intake. So we assume this function for the probability, and we will evaluate this function to see if it makes sense. But basically, it's a nonlinear function that decreases or increases as n increases. All right. By the way, if you look at the actual paper, there is an error. What happened is we had created the document in LaTeX. They wanted it in Word. We had to convert it. When we sent it to them, they messed up some of the equations. Anyway, so A and B are parameters which we need to set, and these determine the shape of the curve. So given this probability, the number of graduates as a function of n is then given by g of n here, which is n over 1 plus e to the n minus a over b. So this is how it would look as a simple example. So on the left, we have the student intake and we have the dropout probability, P of n. So as the number of students you bring in increases, as I said before, there are two effects. The quality will drop, average quality will drop, which means the dropout rate would increase, which means the amount of work wasted would increase, which means the overall dropout probability would increase as well. So it's a nonlinear effect. And on the right, we have the relationship between graduating rate or graduating students as a function of student intake. All right, so there is an optimal point. As you add more and more students, yes, you graduate those students, but at some point you start, this is, the overload control problem, that the good put starts to decrease as the load increases. In this particular case, the optimal intake is about 3,500 students. Now, this is assuming the resources available remain constant. Of course, if you add students and you increase resources, then yes, things will be different. So we wanted to validate this model, and so we took information. This is public information from a university's website, and of course you know which university it would be. So we took we used publicly available data, but so we were able to get the intake from the website, the number of students enrolled, but we couldn't get specific information about which student. Some students take 3 years, some take 4 years, etc. So we just assumed that all students graduated after 3 years, which is not entirely correct, but it's an assumption we had to make. With more detailed data, we could do a better job. The PN was then computed as a number, as a function of the number of students who dropped out, divided by the intake, right? So that's the probability of somebody dropping out. And this was obtained over several years, and then we did nonlinear regression to obtain the parameters A and B. And so this is what we got. So there were the university had 3 campuses, so we evaluated each campus separately. Now, again, it would be better if we could do this on a per faculty basis or even a per department basis, because it will give us better information, but we had to do it on the overall university enrollment. So on the left, we have dropout probability as a function of intake, and we do see this nonlinear effect. We did have an outlier, which is when we looked into more detail, it was because of COVID. And we see this on the right-hand side. If you look at the case of graduated students as a function of intake, we see a sudden drop for red, and it turns out that year happens to be the COVID year. So that's the year where things were stopped completely, and so students couldn't graduate. And that's why we have this outlier there. But here we could see that the, we could find the maximum intake, etc. So this is campus 1. This is for campus 2. And we again saw outliers here. So that blue mark and that red mark. It turns out for this particular campus, those the blue point and red point corresponds to 2 events. One event is when the campus decided to stop subsidizing fees. All right, and some of you probably know which campus that is. They stopped subsidizing fees, which meant enrollment dropped significantly. And then a few years later, they increased, they reinstated reimbursement of or subsidizing student fees. And we clearly saw those 2 years as being outliers. All right. But again, we found, you know, a similar relationship with student intake and graduating rate. And then the final campus, what we found is that they had not, there was an issue with high dropout rates, right? So the dropout rate was on the order of 25%. So there was an issue there with even dropout rate. So they need to solve that issue first before doing this optimization stuff. We also looked at Oxford University, which also had data. And here, so this is a public university, but of course they are concerned about reputation. So they will not allow the dropout rate to be too high. So their dropout rates is on the order of 10%. And if you look on the left, we see the dropout probability as a function of intake. And then on the right, we see that the same sort of relationship between graduated students and student intake. Here, they are relatively within a narrow range of intakes, because within that range, the graduating rate is about the same. All right, so this was just a simple exercise. I just wanted to see if my intuition that there was a relationship between graduation rate and enrollment rate, and if modeling it as an overload control problem made sense, and so it did. All right, so that's one paper. Yeah, law. Yeah, Sophia says it's a law of diminishing returns. So it does, you know, it does say a couple of things. You know, if we want to, if our concern is graduation rates, which is what we should be concerned about, then we have to be careful as to how we increase enrollment. We don't want to do it arbitrarily. So that's one paper, and then the final paper. Are we doing on time? Oh, final paper is all right. This one. So we've talked about this kappa algorithm over the past few you know, several papers. One of the issues we kept talking about is the computation time to compute the optimal kappa. All right. So initially, what we did is, you know, we did a linear search over kappa to find the optimal value, but we've been working on ways to speed things up. And one way, well, we're looking at multiple fronts. One is a good initial guess for optimal kappa, because the optimal kappa depends on you know, basically 3 factors: the personalization, which is reflected in sort of trending information. It depends on the noise, or that could be translated into sort of like the coefficient of variation, and the density of samples, which gives you the level of how far you need to go to capture enough information. So using those factors, we could come up with a good estimate, and so Kevin actually is working on using those statistics to come up with a good initial guess. But even with that initial guess, we've been looking at ways to speed things up, and this is one way. So so I won't go over this in much detail because we've done this several times before, but So let's look at a single feature, age, and look at how we would do imputation and prediction of the labels for this feature age. Should I go over this again? Well, this morning I went over some of this. I know some of you are new, so let me just kind of spend some time on it. So if you have a test sample, so we have a training set and a test set. If you have a test sample, there may be few or no training samples with feature value corresponding to that test sample, right? So we may need to impute or do a better prediction for that particular test sample. One way to do that is by aggregation over years. You could group individuals or samples by years, etc. But then you have to figure out, well, what's a good best grouping, etc. Here we provide a different approach. We use this weighted average of all samples to predict the label of or the target value of the test sample, and the kappa is used to represent the rate of decay of the weighting. To get kappa, we use k-fold validation, measure the mean square error for a given kappa, vary that kappa, and see what value gives you the lowest mean square error. As we said before, in the extreme cases where kappa equal to 0, that corresponds to averaging over all samples, which means that we are simply ignoring the feature because it doesn't help. There's too much noise. And as kappa goes to infinity, if there are at least one sample, training sample corresponding to the test sample in terms of that feature, then as kappa goes to infinity, you go to the average value of that of the tag value over all samples with the same feature value of the test sample. All right, so you get fully personalized in the case of kappa going to infinity. If there are no samples, test samples, and you have to impute the limit, what happens is that you converge to the average target values for samples closest to that test sample target value, test sample feature value. Now, so what we found over, after looking at several of these curves, the mean square error is a function of kappa, or sometimes the mean absolute error, depends on what we plot, but typically has the same curve. It's initially convex, and then it becomes concave, and then it goes to some limit, and we could show that there's a limiting value there. In fact, the limiting value is based on the totally personalized case. So we haven't been able to prove that the function is always of this form, but we believe we eventually will be able to prove that it has this form. Now, using this information, we know that the minimum lies in the convex area. So we could make use of that information by trying to stay within the convex region, first of all. All right, so if kappa is in the concave region, we decrease it to get into the convex region. And then once we're in the convex region, we could do a better job at optimizing. All right, and so the way we do that is we take three values of kappa. And so, for instance, 0 is one valid value. We could use a very large value and something in between. We form a quadratic function between these 3 points, determine the minimum of that quadratic, and use that new minimum point as our next value. So then we compute the corresponding MSE for that particular kappa. All right. So now hopefully we have a new kappa value that is closer to the optimal. We then take the 3 closest points or the 2 closest points to that value, form a new quadratic equation, etc. So it's like successive quadratic approximation, but slightly different here because it's with quadratic approximation you're making certain other assumptions. With successive quadratic approximation. So if the new quadratic is convex, we repeat the process. If it's not, then we know we're in the concave region, so we move to the left, and so we include all that in the algorithm. All right, and of course, we talked about how you would apply this with multiple features. It's just a combination of the Euclidean distance of the by combining the distances of the individual features. So here is an example of this quadratic approximation with 6 features. So it's an insurance example where the tag value is the average claim rate per year. And the red dots here correspond to the what I just mentioned. So after about 3 iterations, you already get to the range where you're almost close, well, very close to kappa. All right. So after about 3 iterations, or actually it's like 2 iterations, you get to where you want to get without having to evaluate over multiple kappa values. So if we're able to get a good first value for kappa, we could take that initial value, take 2 other values close to that, maybe plus or minus 1 from that value, form this quadratic, and repeat the same process, and we should be able to get to the optimal even faster. So we hope this would speed things up in terms of max optimizing over kappa. This is just the how the kappa converges. So you see it starts off high, it goes to 8.9, then it comes back up, and then it converges to the optimal value. All right, so we try this with different examples. We need to prove convergence, and the initial points are important. And as I said, we are looking at coming up with good initial points. And this regression algorithm has been shown to perform well. One thing to note is, optimizing over kappa. How are we doing on time? Oh, almost 4. Optimizing over kappa may take some time, but you only need to do this when you do training. All right. So let's take an insurance company. All right. They want to let's use this. Suppose they want to use this approach to optimize risk by by looking at claim rate information. Maybe every 6 months or maybe every 3 months, they will take the entire data set, do all the training for kappa, etc., and then use those kappas to evaluate new customers from then onwards. Evaluation is very fast. It doesn't require any kind of training. You just plug in all the kappa values, do the weighted average, and you get a prediction for that customer. So it's extremely fast. What's slow is the optimization of a kappa, but as I said, that's only done infrequently, because you don't want to do it on a daily basis because things don't change that fast. So maybe every 3 months you will throw out the oldest three months worth of data, you would add the latest 3 months worth of data, and you would recompute the kappas, and the kappas would already be close to what you had before, so you just have to search around The kappas will already be close to optimal, so we don't need to search very far. So yeah, so I don't see optimizing over kappa as being a big deterrent to using this. But still, we want to improve on how fast you could do it, especially when you have large data sets. So that's this talk. Sorry about that. And yeah, so that's it for today. I think that was the last talk. Thanks for showing up. Before we leave, anybody have any questions about any of the papers or on any anything about TTLAB or anything whatsoever? Please feel free to ask at this point. So yeah, just I see we have some visitors here. So hi Trevor Dean. I know Trevor from way back at when he was at TSTT.
Hi, Patrick. Good seeing you.
Same
Keep
here.
up the good work.
Thanks. And if anybody else wants to introduce themselves to us, feel free to do that. I don't want to point people out, because, some people may not want to do that. But as I said, TTLAB is always looking to collaborate with people. As you see, we do a wide range of work on a wide range of topics from, from this morning, you saw stuff on eSIM pricing. Then we talked about physics and we talked about regression, etc. So it's a wide range of problems we work on. And we always want to work on practical problems. So we always seek out problems in industry. And as you can see, most of the problems we've worked on are industrial problems. Some of them have actually been deployed within that particular company. But we also do some more theoretical stuff like this kappa algorithm, which eventually, we'll deploy in such a way that companies could use as well. We just have to show that it actually is powerful, as good as we think it is. But yeah, we're always looking for collaborations. Not only with industry, we would like to do more with government, but that hasn't turned out to be the case. We do quite a bit of work with CSOs, civil society organizations, like Cropper Foundation, but we haven't been publishing as much in those cases, and we want to push that envelope as well. So I don't want to keep people too long. It's 4 o'clock Trinidad time. Any questions before we close off? You're welcome, Safia. All right, if there are no questions, thanks again for showing up and supporting students. I think they enjoyed presenting, and it's good for them to present, to practice. So thanks for showing up as an audience. And what we plan to do is next, we used to have this on a monthly basis. So every month we would have like 2 presentations, which was better, more relaxed. We haven't done that in a while, and that's why we had to do this year-end thing for 2023. When I saw that we did so much work this year, I thought it would be nice to present it. So that's why we have this kind of all-day session, because of having stopped the monthly sessions. But we plan to restart the monthly sessions next year. So every month we'll probably have 2 or 3 presentations, and it will be more relaxed because we wouldn't have to rush in 15-minute slots. So just look out for us, on Facebook or on LinkedIn, wherever we post stuff. And hopefully I'll see some of you there. All right, so that's it for today, and thanks again, and bye everybody.
Bye. Thank you, everyone.
Thanks, Sophia. Bye, Alana.
Hey, Prof, we doing office hours tomorrow?
Yeah, I'm gonna do office hours tomorrow. I know we have some things to discuss, right? I forget what it was.
Yeah, I mean, I want to talk about the kappa estimate. Any reason we don't normalize Y when we're doing it?
Well, Y is the target value, right? So, so distance in that space shouldn't matter, right? You see what I mean?
Yeah, it just
Because
seemed like it's stabilizing my estimate for kappa because I don't have as much variation on that side.
well, no, I know we normalize on the x-axis on the feature value,
Yeah,
right? But you're talking about normalizing on the target
Y
value.
as well. Yeah.
Because, but so because all right, so distance would be in difference there. So when we take the Euclidean, it shouldn't matter, right? Because I'm trying to see why it wouldn't matter. If you take the Euclidean, right? So Euclidean distance, and then we take in. Oh, you're talking about the fact that if we do that, we could keep the kappa range in the final prediction. That's what you talk about in the final prediction. So just like we normalize for the individual features, if we normalize for the final prediction, we might keep kappa in a smaller range.
Yeah,
That's what you're saying?
Yeah.
Yeah. So, but we could do that at the end, right? So we compute distances, and at the end, yeah, just normalize. Yeah, because the kappa, yeah, you're right. Just like we normalize for the individual features, if we normalize for the final thing, we should maintain kappa in a smaller range of values. Yeah, that makes sense. I see now.
Okay, yeah, I'll try it because with the window it varying, yeah, depending on the window. So while it does capture the variation, I don't know what to do. I mean, we can talk about this tomorrow. I know he was out all day, so
Yeah, I'm not breakfast yet, so
yeah.
but yeah, so you know, and if you think we'll take an hour tomorrow, then yeah, schedule an hour.
Yeah.
Because I really want to get that classification stuff out, because yeah, and we, yeah, with the classification, and I had asked Deepak to look at the multi-class case, but I think he will need some help. So if you could take the lead on that and have him, you know, kind of pull the data together and stuff like that. But let me see what he gets first, and
Yeah, I don't mind because I was thinking what we could do if you want, we could take the initial paper for the base, maybe submit it to a conference, and then do the full blown thing and submit it to a journal since we get a little pressure to submit it as a journal.
yeah, well, so let's wait on this outcome from this journal and see. So that one, so that classification problem, and I forget completely. The one we did is using naive Bayes, is a naive Bayes, but we use the kappa stuff to do the imputation to avoid the zero frequency problem.
Yeah, but we didn't do the initial encoding.
Oh, so we didn't do the initial, we didn't even do the final encoding. We used naive Bayes for the final.
Yeah, well, we use the distance with the kappa as a proxy, basically, for the probability. Yeah, but we went to encode it initially there.
So we could get, and since we're already getting better results, of course, we shouldn't be able to do, we can't do worse, right? So,
Yeah, I'm pretty sure it'll be much better.
yeah. So that would be, and so yeah, so what you're thinking is we should submit this present paper to a conference and then
Do the full thing in the journal.
but we waited to hear from this final journal, right? This recent journal.
I don't think we have any at the moment. The last one we didn't resubmit since.
All right, so let's do it for a good conference and then expand on it for the journal to get it out. So we can discuss this tomorrow, which conference, etc. Yeah. I mean, it's a lot of little things we could do, you know, but I know you already have your plate full, right? So, so yeah. But yeah, I think it went well.
Yeah.
And I think, yeah, so from January, and we'll figure out when in January we'll have the first one, but yeah, we'll do the monthly things.
Yeah, no meeting at 8 today, right?
Oh yeah, no meeting. Yeah, no meeting today. I figured, yeah, we already had this thing all day, so yeah, I'll cancel the. In fact, I think let's cancel until the end of the year and then start back next year. Because next week I will be gone. I'll be in Florida, I think. So it might be a little difficult. And then the following week is Christmas. The week after that is New Old Year's kind of thing. So yeah, so we'll put it on hold until I'll send a message out about no more meetings. All right. All right, good. I see, Gabri, you wanted to say something because I see you still on. Gabri?
No, I don't want to say anything.
Oh, okay. All right. Well, we kind of closing off now.
Okay.
All right.
Bye.
Okay, Kevin. All right. So tomorrow.
Yeah.
Okay.